Right now, approximately 50 million miles from where you sit, a world smaller than some moons is tearing itself apart from the inside. Its surface, scorched to temperatures that would melt, lead on the sunlit hemisphere and frozen to nearly absolute zero in eternal shadow, is fracturing along thousand-mile faults as the entire planet slowly, relentlessly contracts. In the time it has taken human civilization to rise from scattered hunter-gatherer bands to a species capable of launching spacecraft toward other worlds, this ancient body has shrunk by roughly a mile in diameter. The cracks spreading across its cratered face are so vast that they cast shadows visible from orbit, cliffs taller than any mountain range on Earth cutting across terrain older than the first single-celled organisms to emerge in our oceans. This is Mercury, and almost no one talks about it. Here is what will fundamentally rewrite everything you assume about the inner solar system. The planet closest to our Sun is not a dead, airless rock waiting in cosmic irrelevance while we fixate on Mars and the outer planets. It is a world in active transformation, a planetary-scale laboratory demonstrating processes we are only beginning to understand. Its surface bears witness to a catastrophic history of bombardment, volcanism, and tectonic upheaval that challenges our models of planetary formation. Its core, proportionally the largest of any rocky body we know, generates a magnetic field that by all rights should not exist. And for the past 15 years, two extraordinary spacecraft have been systematically uncovering a Mercury that textbooks written a generation ago could never have predicted. The smallest planet in our solar system is also one of its greatest remaining mysteries. If you find yourself curious about this overlooked world at the edge of the Sun's domain, and enjoy content that reveals the cosmos as it truly exists, then please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. The first thing you must understand about Mercury is that we almost forgot it existed. This is not hyperbole. Among the planetary science community, a quiet consensus held for decades that Mercury was simply uninteresting. Venus had its crushing atmosphere and runaway greenhouse effect. Mars had its ancient riverbeds and the tantalizing possibility of past life. The outer planets offered moons with subsurface oceans, geysers erupting into space, and hydrocarbon lakes under orange skies. But Mercury sat there in its tight, swift orbit, seemingly offering nothing but a smaller, more battered version of our own moon. Airless, geologically dead. A footnote in solar system studies. The last time any spacecraft had visited Mercury before 2011 was March 16th, 1975, when Mariner 10 made its third and final flyby after runs in 1974. In the decades that followed, we sent orbiters to every other planet in the solar system multiple times. We landed rovers on Mars, dropped probes into Jupiter's atmosphere, achieved orbit around Saturn, and observed Titan's methane weather systems. We dispatched New Horizons on its 9-year journey to Pluto, and Mercury received precisely nothing. For 33 years, our entire knowledge of the innermost planet rested on images captured by a spacecraft designed with 1960s technology, pictures that mapped only 45% of the surface and revealed it in resolutions that left entire geological provinces as nothing more than grey smudges. Consider the implications of this neglect. A human born when Mariner 10 made its final flyby would have been old enough to have children of their own before another spacecraft returned to Mercury. An entire generation of planetary scientists built their careers without a single new data point from the planet closest to the Sun. The textbooks hardened into orthodoxy. Mercury was a dead world, its geological story over billions of years ago, its surface nothing but a record of ancient cosmic violence. And yet the very features visible in Mariner 10's grainy images should have told us something remarkable was happening. Because stretching across Mercury's cratered surface were structures that could not be explained by impact bombardment alone. Cliffs hundreds of miles long, cutting across craters and ancient lava plains with indifferent power. Not crater walls, not volcanic ridges, something else entirely. Something that suggested the entire planet was shrinking like a cooling, wrinkling apple left too long in the sun. These are the Lebate scarps, and they would eventually reveal Mercury to be one of the most geologically active worlds in the inner solar system. To understand what a Lebate scarp is, you must first picture the forces acting on a planet as it cools. All rocky worlds begin hot. The violence of formation, the rain of debris during planetary accretion, the radioactive decay of heavy elements trapped in the core, all of these processes generate tremendous heat. A newborn rocky planet is largely molten, its interior churning, its surface a hellscape of magma seas and volcanic eruption. Over time, measured in billions of years, this heat radiates away into the cold vacuum of space. The world cools, and as it cools, it shrinks. The physics is straightforward. Hot material occupies more volume than cold material of the same mass. As a planetary interior loses thermal energy, its atoms pack more tightly together. The entire body contracts. But here is where the process becomes interesting. A planet's surface, exposed to the frigid emptiness of space, cools and solidifies far faster than its deep interior. The crust hardens into a rigid shell, while the mantle and core beneath it remain hot enough to continue contracting. What happens next is inevitable. The solid crust, no longer able to shrink smoothly with its interior, must accommodate a decreasing underlying volume. It fractures, it folds, it thrusts upward along fault lines as the planet literally collapses inward. The result is a lobate scarp, a sinuous cliff formed when one section of crust is pushed up and over an adjacent section. The fault responsible is called a thrust fault, and it produces landscapes that would be difficult to conceive if we had not seen them with our own eyes. Imagine standing at the base of such a feature on Mercury. Rising before you is a wall of grey, fractured rock reaching 1 to 2 miles into the black sky. The cliff face stretches to either horizon, curving gently with the planet's surface, extending for 300 miles in each direction. There is no atmosphere to soften its edges, no erosion to wear it down. The scarp stands in perfect, brutal clarity, precisely as it did when the fault that created it last slipped perhaps 50 million years ago, perhaps more recently. We do not yet know for certain. Mariner 10 photographed several of these scarps in the 1970s, and their presence raised immediate questions. Labatt scarps on the Moon are generally small, localized features associated with local tectonic adjustments. But Mercury's scarps were enormous, distributed globally, and cut through terrain of every age, from the oldest heavily cratered highlands to relatively younger smooth plains. This distribution pattern could only mean one thing. The thrust faulting responsible for these scarps was not local, it was planetary. The entire world had been contracting, and that contraction had been ongoing for billions of years. The Mariner 10 data suggested Mercury had shrunk by roughly 1 to 2 kilometers in radius since its crust solidified. This was already more than expected. Rocky planets in our solar system are supposed to be geologically dead by now, their heat long since dissipated, their tectonic activity a distant memory. The presence of such extensive thrust faulting on Mercury hinted that something about the planet's interior, something about its enormous core, was keeping the cooling process active far longer than standard models predicted. But the Mariner 10 data covered less than half the planet. The scarps scientists could study were merely the ones that happened to fall within the spacecraft's limited field of view during its 3 brief flybys. For all anyone knew, the unseen hemisphere was smooth and featureless, or perhaps covered with even more dramatic tectonic structures. There was no way to tell. For 3 decades, that uncertainty stood as one of the great frustrations of planetary science. Mercury sat in plain sight, closer to Earth than most of the targets we sent missions to explore, yet it remained more mysterious than moons orbiting planets billions of miles away. The innermost planet had become, paradoxically, one of the most difficult to study. And the reason for that difficulty reveals something profound about orbital mechanics and the challenges of interplanetary exploration. Getting to Mercury is, to use technical terminology, extraordinarily hard. This statement surprises most people who encounter it. Surely they assume flying toward the sun should be easy. Everything in the solar system is, in a sense, falling toward the sun already. Our own Earth orbits at roughly 18 miles per second simply to maintain its distance from that massive gravitational well. To reach Mercury, you merely need to fall a bit deeper, let gravity do the work, and coast inward toward the smaller planet's orbit. This reasoning sounds plausible, is also almost entirely wrong. The difficulty lies not in reaching Mercury's orbit, but in staying there. Our planet moves through space at 67,000 miles per hour. Mercury, closer to the Sun, moves at an average of 105,000 miles per hour, making it the fastest planet in the solar system. A spacecraft launched from Earth carries Earth's orbital velocity as a starting inheritance. To match Mercury's orbit, that spacecraft must shed most of this inherited speed, while simultaneously diving deep into the Sun's gravitational potential well. A well that will accelerate the spacecraft dramatically as it falls inward. The result is a challenging paradox. You want to slow down, but everything around you is trying to speed you up. Chemical rockets, the workhorses of spaceflight since the 1950s, struggle with this task. The amount of fuel required to perform the necessary velocity changes would make any Mercury mission prohibitively expensive. The solution that engineers developed involves something far more elegant: gravity assists. By carefully flying past other planets and allowing their gravitational influence to reshape the spacecraft's trajectory, mission designers can gradually lower a probe's orbit toward Mercury without expending enormous amounts of fuel. But this elegance comes with a cost measured in time. Many years of time. The Messenger spacecraft, which would eventually become the first probe to orbit Mercury, launched from Earth on August 3, 2004. It did not arrive at Mercury until March 18, 2011, nearly 7 years of flight. During that period, Messenger performed 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself, each gravitational encounter nudging the spacecraft onto a trajectory slightly closer to its final goal. The path covered approximately 4.9 billion miles, roughly the same distance as a trip to Neptune, simply to reach a world that at its closest approach sits only 48 million miles from Earth. The circuitous route was not inefficiency, it was necessity. There is no shortcut to the planet closest to the Sun. When Messenger finally entered Mercury orbit on that March day in 2011, it carried the accumulated hopes of a scientific community that had waited a generation for this moment. The spacecraft's name stood for Mercury Surface, Space Environment, Geochemistry and Ranging, an acronym engineered with unusual care because the mission designers understood that this probe would be delivering messages from an unknown world. What those messages revealed would force a fundamental revision of everything scientists thought they understood about Mercury. The global mapping that Messenger conducted in its first months of operation revealed a planet covered in lobate scarps far more extensively than Mariner 10's partial coverage had suggested. The thrust faults were everywhere. They crossed every type of terrain, indicating that planetary contraction had been continuous throughout Mercury's geological history. More importantly, Messenger's high-resolution cameras captured something Mariner 10 could never have detected: small scarps, far younger than the giants observed in the 1970s, scarps that cut across impact craters so fresh that they could only be tens of millions of years old. In geological terms, tens of millions of years is yesterday. The presence of these young features meant that Mercury was not a fossil world whose tectonic activity ended billions of years ago. It was still contracting, still shrinking, still alive. The new data forced scientists to revise their estimates of Mercury's total shrinkage dramatically upward. Where Mariner 10 data had suggested 1 to 2 kilometres of radial contraction, Messenger's comprehensive survey indicated the planet had shrunk by approximately 7 kilometres in radius since its crust solidified. This means Mercury's circumference is now roughly 44 kilometres, about 27 miles, shorter than it was 4 billion years ago. The planet has lost enough volume to make room for a sphere the size of a small moon within the space its former self once occupied. And this contraction continues. The younger scarps Messenger photographed may represent fault movements within the past 50 million years, perhaps even more recently. Mercury's interior is still cooling, still shrinking, still forcing its rigid crust to accommodate an ever-diminishing core. In the endless silence of the innermost solar system, cliffs are rising, cracks are spreading, and a world written off as geologically dead is proving itself very much in geological motion. To grasp why Mercury's contraction has been so dramatic, you must look beneath its battered surface to the extraordinary core that defines this world's identity. Mercury is, in a very real sense, more core than planet. While Earth's iron-nickel core makes up roughly 32% of our planet's total volume, Mercury's core accounts for approximately 85% of the planet's volume and about 70% of its total mass. If you could slice Mercury in half, you would see a thin shell of rocky mantle and crust surrounding an enormous metallic sphere nearly 1,500 miles in radius. The planet is, in effect, a ball of iron with a thin rocky veneer. No other known rocky body in our solar system has such proportions. Mars's core is roughly 42% of its volume. Venus is thought to be similar to Earth. Even the Moon, small as it is, maintains more reasonable core-to-mantle ratios. Mercury stands alone as the iron planet, a world whose internal structure looks nothing like what we would expect from standard models of planetary formation. How Mercury ended up this way is one of the great unsolved problems in planetary science. Several hypotheses have been proposed, each with supporting evidence and unresolved difficulties. The most dramatic suggests that Mercury was once a much larger planet, perhaps twice its current size, with normal core-to-mantle proportions similar to Earth's. Early in solar system history, this proto-Mercury suffered a catastrophic giant impact that blasted away most of its rocky mantle and crust, leaving behind only the dense iron core and a thin surviving shell of silicates. This hypothesis elegantly explains Mercury's odd density and composition, but it requires an impact of almost inconceivable violence, and the current surface does not show the clear evidence of such an event that scientists would expect. An alternative hypothesis proposes that Mercury formed close to the young Sun, where temperatures were high enough to prevent lighter silicate materials from condensing and accreting onto the growing planet. In this scenario, the protoplanetary disk in Mercury's formation zone was naturally enriched in iron-bearing compounds, and the planet simply grew with the composition its local environment allowed. This explanation avoids the need for a giant impact, but struggles to explain certain chemical signatures MESSENGER detected on the surface, signatures that suggest Mercury's mantle contains volatile elements that should have been driven away by such extreme formation temperatures. A third possibility involves a complex interaction between the young Mercury and the violent radiation of the infant Sun. Solar wind and radiation pressure from a young star can strip away lighter elements from forming planets, potentially leaving behind a metal-enriched body. This mechanism is plausible but poorly constrained, and simulations struggle to reproduce Mercury's exact properties. What we know for certain is that Mercury ended up with an oversized core, and that core is responsible for many of the planet's most distinctive features. Its enormous iron interior, slowly solidifying as it cools, releases latent heat that drives the continuing contraction MESSENGER documented. The crystallizing inner core also generates the convection currents responsible for Mercury's magnetic field, a field that, frankly, should not exist. Earth's magnetic field arises from the dynamo effect, convection currents in the liquid outer core, driven by heat escaping from the solid inner core, create organized flows of electrically conductive molten iron. These flows generate electrical currents, which in turn produce magnetic fields. The field is weak but significant, strong enough to deflect the solar wind and protect our atmosphere from being stripped away over geological time. Earth's dynamo works because our planet is large enough to retain significant internal heat, keeping the outer core molten and convection active billions of years after formation. Mercury is far smaller than Earth. Standard models of planetary cooling predicted that Mercury's core should have solidified completely billions of years ago, eliminating any possibility of a magnetic dynamo. A frozen core cannot convect. No convection means no organized fluid motion. No organized fluid motion means no magnetic field. The prediction was clear. Mercury should be magnetically dead. Mariner 10 discovered otherwise. On its first flyby in 1974, the spacecraft detected a weak but unmistakable global magnetic field centered on Mercury's axis. The field was roughly 100 times weaker than Earth's, but it was there, it was organized, it was dipolar. It was evidence of an active dynamo generating magnetic forces through convection in a liquid core that, according to prevailing theories, should have solidified long ago. This discovery posed a problem that planetary scientists spent decades trying to solve. How does a planet as small as Mercury maintain an active magnetic dynamo? The answer, MESSENGER eventually helped reveal, lies in the composition of Mercury's core. Pure iron solidifies at a predictable temperature under a given pressure. But iron alloyed with lighter elements like sulfur, silicon or carbon has a much lower melting point. MESSENGER's measurements of Mercury's gravitational field, combined with observations of how the planet responds to tidal forces from the Sun, allowed scientists to determine that Mercury's outer core remains liquid today. The core has not frozen solid because it contains enough sulfur, perhaps 6 to 8% by weight, to significantly lower its melting point. The liquid outer core persists, convection continues, and the magnetic dynamo remains active despite Mercury's small size and ancient age. This finding transformed Mercury from a puzzle to a key. The planet became a natural laboratory for studying how magnetic dynamos operate in conditions very different from Earth's. Mercury's weak field, offset significantly northward from the planet's centre, for reasons still under investigation, challenges dynamo models calibrated to our home world. Understanding why Mercury's field behaves as it does will help us understand magnetic field generation across the solar system and beyond, potentially illuminating how exoplanets around distant stars might protect, or fail to protect, their atmospheres from stellar radiation. The magnetic field is not Mercury's only protection against the Sun's violence. It is, in fact, a woefully inadequate shield, too weak to hold off the solar wind the way Earth's magnetosphere does. What Mercury does have is a tenuous envelope of atoms kicked up from its surface by solar radiation, a structure so thin that scientists hesitate to call it an atmosphere. They use instead the term exosphere, a collection of atoms so sparse that they rarely collide with one another, instead following individual ballistic trajectories before falling back to the surface, escaping into space, or being swept away by the solar wind. Messenger mapped this exosphere in unprecedented detail, discovering sodium, potassium, calcium, magnesium, and other elements dancing above Mercury's surface in patterns shaped by solar radiation, meteoroid impacts, and the sputtering effect of charged particles from the Sun. The exosphere is constantly replenished and constantly lost, a dynamic equilibrium maintained by the relentless processes acting on the planet's exposed face. Mercury, in a sense, is slowly evaporating, its surface atoms drifting away into the solar wind, a process that has been ongoing for 4 billion years. But the surface itself endures, a record of Mercury's violent history written in craters, lava plains, and the great tectonic features that tell the story of a shrinking world. The craters are what most people picture when they imagine Mercury, a battered grey surface that could easily be mistaken for the moon in a casual photograph. This resemblance is not coincidental. Both worlds lack atmospheres that could burn up incoming debris, and both have surfaces composed of similar silicate materials, darkened by space weathering over billions of years. But the resemblance is superficial. Mercury's craters tell a very different story from the Moon's when examined closely. The largest impact structure on Mercury is the Caloris Basin, a circular scar roughly 1,500 kilometres in diameter that dominates the planet's northern hemisphere. The impact that created Caloris occurred approximately 3.9 billion years ago, during a period of intense bombardment that affected the entire inner solar system. The collision was violent enough to send shockwaves through Mercury's entire body, and directly opposite Caloris, on the other side of the planet, lies a region of chaotic, disrupted terrain called, appropriately, weird terrain. Scientists believe this chaotic jumble formed when seismic waves from the Caloris impact converged on the antipodal point, focusing enough energy to shatter the surface on the far side of the world. But Caloris is not merely an ancient scar. Messenger revealed that the basin floor is covered in volcanic plains younger than the impact itself, lava flows that welled up through the fractured crust and filled the enormous depression long after the collision. The basin floor is also crossed by tectonic features, wrinkle ridges from compression, and grabens from extension, indicating complex geological processes active well after the impact event. Caloris is not a static memorial to ancient violence. It is a palimpsest, layer upon layer of geological history overwriting itself across billions of years. Beyond Caloris, Messenger mapped volcanic plains covering vast swathes of Mercury's northern hemisphere. These plains, some of them multiple kilometres thick, represent eruptions on a scale difficult to imagine. Billions of years ago, Mercury was a world of fire as well as iron, its surface periodically reshaped by volcanic outpourings that buried older terrain under floods of molten rock. The volcanic activity eventually waned as the planet's interior cooled, but the plains it created remain, testimony to a young Mercury that was as dynamic as any world in the solar system. Scattered across these plains and the older cratered terrain are structures that represent some of Messenger's most intriguing discoveries, hollows. These are shallow, irregular depressions with bright interiors and halos of high reflectance material surrounding them. They appear fresh, with crisp edges unmarked by subsequent impacts. They cluster on crater floors, crater walls, and other areas where relatively recent processes have exposed subsurface material, and they have no equivalent anywhere else in the solar system. The leading hypothesis is that hollows form through sublimation, the direct conversion of solid material to vapour without passing through a liquid phase. Some volatile substance in Mercury's crust, protected from the sun's heat by overlying rock, is exposed when impacts excavate fresh terrain. The intense solar radiation then causes this volatile material to sublimate directly into space, leaving behind the hollow depressions. The process must be geologically rapid, perhaps ongoing today, because the hollows appear so fresh. But what volatile could survive on Mercury, a world where daytime surface temperatures reach 800 degrees Fahrenheit? The leading candidates include sulfur compounds and chlorine salts, materials that might persist in Mercury's interior, where temperatures remain lower but would rapidly volatilize when exposed at the surface. The hollows are evidence of active geological processes on a world long assumed to be static, and their mere existence challenges our understanding of volatile retention in the inner solar system. The landscape Messenger revealed is one of profound contrast and unfinished business. Mercury's day side, bathed in solar radiation roughly 7 times more intense than what reaches Earth, bakes at temperatures that would melt zinc and lead. The surface rocks glow faintly in the infrared, radiating heat back into space, while shadows cast by crater walls and scarps create pockets of absolute cold mere feet from the scorching sunlight. The temperature difference between a sunlit rock and its shadow can exceed 500 degrees Fahrenheit across a distance you could reach by extending your arm. Night on Mercury is colder still. With no atmosphere to trap heat, the surface loses thermal energy rapidly after sunset, plunging to temperatures of minus 290 degrees Fahrenheit by the time the long Mercurian night reaches its depths. And those nights are long indeed. Mercury rotates on its axis once every 59 Earth days, but its solar day, the time from one noon to the next, stretches to 176 Earth days due to the planet's 3-2 spin-orbit resonance. This curious relationship means Mercury rotates exactly 3 times for every 2 orbits around the Sun, a gravitational lockstep that extends the experience of day and night to nearly 6 Earth months each. The temperature swings are the most extreme of any planet in the solar system. A sensor placed on Mercury's equator would experience roughly 1100 degrees Fahrenheit of temperature change between noon and midnight, a thermal oscillation that stresses surface materials in ways no earthly analogue can match. Rocks expand in the heat and contract in the cold, a process that over billions of years contributes to the breakdown of surface materials into the fine regolith that blankets the planet. And yet within this hellscape of thermal extremes, water ice exists. This was perhaps Messenger's most startling discovery. Radar observations from Earth in the 1990s had detected highly reflective materials in permanently shadowed craters near Mercury's poles, regions where the sun never shines due to the planet's minimal axial tilt. Messenger confirmed these deposits are water ice, frozen in eternal darkness just degrees of latitude from the hottest surfaces in the inner solar system. The ice deposits are substantial. Current estimates suggest Mercury's polar craters hold between 100 billion and 1 trillion metric tons of water ice. For context, the lower estimate equals roughly 100 cubic kilometres of ice, enough to fill a lake 20 miles long, 20 miles wide, and half a mile deep. The higher estimate is 10 times greater. This ice, shielded from the sun's heat by crater walls casting permanent shadows, has accumulated over hundreds of millions of years from comet impacts, asteroid collisions, and possibly outgassing from Mercury's own interior. The polar ice is not merely a curiosity. It represents resources that future human exploration might potentially utilize, and it poses fundamental questions about water delivery throughout the inner solar system. If Mercury, the most inhospitable of the rocky planets, can retain significant water ice, what does that tell us about the prevalence of water throughout our cosmic neighbourhood? The finding forces reconsideration of assumptions that placed water as something special, delivered to worlds in specific circumstances, rather than as something common, present even in the most unexpected locations. Messenger operated in Mercury orbit for over 4 years, far exceeding its original 1-year primary mission. By the time its fuel ran out and mission controllers allowed the spacecraft to crash into Mercury's surface on April 30th, 2015, it had returned over 270,000 images and transformed Mercury from the solar system's blank slate into a world with a story worth telling. The impact crater created by Messenger's demise, roughly 50 feet across, now joins the billions of other scars marking Mercury's ancient face, a small human signature on a world we had ignored for too long. But the exploration of Mercury did not end with Messenger's final descent. Even as that spacecraft was completing its mission, another probe was taking shape in the clean rooms of the European Space Agency and the Japan Aerospace Exploration Agency. This new mission would carry instruments Messenger could not have carried, ask questions Messenger could not have answered, and continue the systematic unveiling of the planet closest to the Sun. The mission is called Bepi Colombo, named for the Italian mathematician and engineer Giuseppe Colombo, whose calculations in the 1970s made the Mariner 10 flybys possible, and who first recognised Mercury's spin-orbit resonance. Bepi Colombo launched on October 20th, 2018, and has been following its own long looping path through the inner solar system ever since. Like Messenger before it, Bepi Colombo must use gravity assists to slowly reduce its orbital energy until it can enter orbit around Mercury. The spacecraft has performed flybys of Earth, 2 flybys of Venus, and has already completed multiple flybys of Mercury itself, each encounter refining its trajectory and returning tantalizing data about the world it will soon call home. Bepi Colombo is scheduled to enter Mercury orbit in late 2025. When it does, it will separate into 2 distinct orbiters: the Mercury Planetary Orbiter, built by ESA to study the planet's surface and interior, and the Mercury Magnetospheric Orbiter, built by JAXA to investigate Mercury's magnetic field and its interaction with the solar wind. Together, these spacecraft will conduct the most comprehensive study of Mercury ever attempted, building on Messenger's discoveries while pursuing new lines of investigation. The questions Bepi Colombo will address represent the frontier of Mercury science. How is the planet's interior structured in detail, and can we constrain the composition and state of the core more precisely? What drives the curious northward offset of Mercury's magnetic field, and how does the dynamo responsible for that field actually operate? How have the lobate scarps evolved over time, and is there evidence for fault movements within recorded human history? What is the composition of the polar ice deposits in detail, and do they contain organic molecules delivered by comets that might inform our understanding of how the building blocks of life were distributed through the young solar system? These are not idle questions. Each one connects Mercury to broader themes in planetary science and solar system history. Understanding Mercury's core helps us understand core formation in rocky planets generally, including Earth. Understanding Mercury's magnetic field illuminates dynamo processes that protect worlds throughout the cosmos. Understanding Mercury's ice deposits informs our knowledge of water delivery mechanisms that may have seeded Earth's oceans and enabled life to arise. Mercury is not a sideshow. It is not a footnote. It is the first rocky planet, the closest witness to our Sun's 4.5 billion year history, and a world that defies the simple narratives we constructed in the absence of data. The textbooks that dismissed Mercury as geologically dead are already being rewritten. The assumptions that Mercury had nothing to teach us about planetary evolution are already being discarded, and somewhere in the darkness of the inner solar system, cliffs are rising, ice is accumulating in permanent shadow, and a planet smaller than Ganymede is proving that size has nothing to do with significance. The surface of Mercury tells a story written in stone, metal, and the relentless mathematics of thermal physics. To understand what makes this world unlike any other in our solar system, we must look beneath the battered exterior, past the craters and plains, down to the heart of the planet itself. What we find there is not what anyone expected. It is too large, too dense, too dominant, and it is the key to understanding everything strange about Mercury. Every rocky planet in the inner solar system possesses a metallic core surrounded by a silicate mantle and crust. Earth's core accounts for roughly 32% of our planet's total mass. Mars, with its smaller size and lower density, has a core representing perhaps 21% of its mass. Venus, similar in size to Earth, likely has comparable internal proportions. But Mercury breaks the pattern so dramatically that planetary scientists have spent decades trying to explain it. Mercury's iron-nickel core accounts for approximately 85% of the planet's radius. In terms of mass, the core represents roughly 70% of everything Mercury is. Picture a world where the metallic heart has swollen to consume nearly everything else, leaving only a thin shell of rock floating atop an ocean of iron. This is Mercury. Is a planet that is, in essence, an exposed planetary core with a veneer of geology draped across its surface. The numbers bear contemplation. Mercury's core has a radius of approximately 2,020 kilometres. The entire planet has a radius of roughly 2,040 kilometres. This means the silicate mantle and crust together form a shell only about 420 kilometres thick, surrounding a metallic sphere that would itself constitute a respectable world. Earth's core, by comparison, has a radius of about 3,485 kilometres, but our planet's radius is 6,371 kilometres, leaving a mantle nearly 2,900 kilometres thick. The proportions are inverted. Earth is a rocky world with an iron core. Mercury is an iron world with a rocky coating. How does a planet come to possess such bizarre internal architecture? This question has driven theoretical modelling for half a century, and no single answer has achieved consensus. The leading hypothesis involves a catastrophic collision early in solar system history. According to this model, Proto-Mercury was once a larger world with more normal proportions, perhaps 2 to 3 times its current mass. Then, within the first 100 million years of the solar system's existence, a massive impactor struck the young planet with enough energy to vaporize and strip away most of its mantle, leaving behind the dense iron core wrapped in whatever silicate material survived the cataclysm. This giant impact hypothesis draws support from Mercury's observed density and from our understanding of how violent the early inner solar system truly was. The giant impact that formed Earth's moon occurred in this same era, as did countless other world-shaping collisions. Mercury's oversized core could simply be the scar of an ancient violence that stripped away the lighter elements, while the heavy iron remained gravitationally bound. But alternative explanations persist. Some researchers propose that Mercury formed from material already enriched in iron relative to the rest of the inner solar system. The innermost regions of the protoplanetary disk, scorched by the young sun's radiation, may have experienced selective vaporization of lighter silicates, while iron remained in solid form. Under this model, Mercury assembled from building blocks that were simply more metallic than those available farther from the Sun. No giant impact required, merely the natural consequence of forming in the hottest, most extreme environment the disk could offer. A third possibility invokes the solar wind itself. Over billions of years, energetic particles streaming from the Sun may have gradually sputtered away Mercury's original mantle, atom by atom, eroding the silicate shell while leaving the denser core relatively untouched. This process operates far too slowly to account for the current proportions over the age of the solar system, but it may have contributed to ongoing mass loss that compounds whatever primordial process established Mercury's unusual composition. Messenger's detailed gravity measurements allowed scientists to probe Mercury's interior structure with unprecedented precision. By tracking subtle variations in the spacecraft's orbital speed as it passed over different regions of the planet, researchers could map variations in Mercury's gravitational field and infer the distribution of mass beneath the surface. What they found confirmed the dominance of the core while revealing an unexpected complexity. Mercury's core is not simply a solid ball of iron. It appears to possess a solid inner core surrounded by a liquid outer core, similar in structure to Earth's core but with different proportions. The liquid outer core is substantially larger than anticipated, remaining molten despite more than 4 billion years of cooling. This persistence of liquid iron is remarkable given Mercury's small size. Smaller bodies cool faster because they have higher surface area to volume ratios, allowing heat to escape more efficiently into space. Mars, larger than Mercury, has a core that appears to be entirely or almost entirely liquid, with no solid inner core yet detected. Earth, larger still, has both a solid inner core and a liquid outer core. Mercury's ability to maintain a partially liquid core despite its small size suggests either that the core contains elements like sulfur that lower the melting point of iron alloys, or that the mantle acts as an effective insulating blanket trapping heat in the interior. Messenger's data support the sulfur hypothesis. Spectroscopic measurements revealed surprisingly high concentrations of sulfur in Mercury's surface materials, suggesting that sulfur is abundant throughout the planet's composition. A core containing several percent sulfur by weight would remain partially molten at temperatures that would solidify pure iron, explaining how Mercury maintains the liquid layer necessary to generate its magnetic field. The presence of this liquid outer core has profound implications. As Mercury slowly cools, the liquid iron at the boundary between the outer and inner core crystallizes, releasing latent heat and causing the inner core to grow. This process has continued for billions of years and continues today. As the inner core expands, the overlying liquid contracts, and as the entire core contracts, the planet shrinks. This is the mechanism behind Mercury's lobate scarps, the thrust faults that crisscross the planet's surface like wrinkles on a deflating balloon. The core is cooling, the core is crystallizing, the core is contracting, and because the core dominates Mercury's interior, the entire planet contracts with it. The silicate crust, rigid and brittle, cannot shrink smoothly. Instead, it fractures. Great blocks of rock thrust over one another, creating cliffs that can run for hundreds of kilometres and tower a kilometre or more above the surrounding terrain. Consider the physics at work. When iron transitions from liquid to solid, it occupies less volume. The atomic packing becomes more efficient. Each increment of solidification reduces the total volume of the core by a small but measurable amount. Multiply these tiny volume changes across a core 4,000 kilometres in diameter, and the cumulative effect becomes dramatic. Planetary scientists estimate that Mercury has contracted by roughly 7 to 14 kilometres in radius since the end of the late heavy bombardment roughly 3.8 billion years ago. This contraction has generated the most extensive network of contractional tectonic features in the solar system. Discovery rupees, the massive fault system that Mariner 10 first photographed, represents just one example of this global process. Messenger revealed that lobate scarps cover Mercury's entire surface, appearing in every region, at every latitude, with no systematic orientation that would indicate a preferred direction of compression. This global distribution and random orientation indicate that the contraction is planetary in scale, driven by internal cooling rather than regional tectonics. Mercury is shrinking everywhere, all at once, and has been for billions of years. The magnitude of this shrinkage challenges older estimates. Before Messenger, some models suggested Mercury had contracted by only 1 to 2 kilometres in radius. The spacecraft's comprehensive imaging revealed far more contractional features than anyone anticipated, forcing upward revisions of the total shrinkage. More recent analyses place the minimum contraction at 7 kilometres, with some estimates reaching 14 kilometres or more. These numbers carry uncertainty, but the conclusion is robust. Mercury is not subtly adjusting. It is dramatically diminishing, and the process has not stopped. Analysis of small-scale features on lobate scarp fault faces reveals evidence for recent, possibly ongoing fault activity. Some scarps display pristine morphology that would be degraded by billions of years of micrometeorite bombardment. Some show evidence for multiple episodes of fault movement, suggesting repeated slip events rather than a single ancient displacement. The planet appears to be tectonically alive, albeit in a manner fundamentally different from Earth's plate tectonics. Earth's crust is broken into plates that move horizontally, creating earthquakes at their boundaries. Mercury's crust is intact but under compression from within, potentially generating Mercury quakes as faults slip in response to the relentless shrinking of the core. Detecting these potential Mercury quakes presents extraordinary challenges. Earth's seismic activity is monitored by thousands of stations, distributed across every continent. Mercury has no seismometers on its surface, and no current mission plans include deploying them. We infer tectonic activity from the youthful appearance of certain features and from theoretical modelling of the cooling process. Direct detection of Mercury quakes remains a goal for future exploration, perhaps achieved by a lander mission carrying seismic instruments that could listen to the planet's interior for years or decades. The lobate scarps reveal another unexpected truth about Mercury. Many of them cross-cut impact craters, meaning the faults formed after the craters were created. By analysing which scarps cut which craters, and by dating those craters using statistical crater counting techniques, scientists can establish a rough chronology of fault activity. The results indicate that scarp formation has continued throughout Mercury's geological history, from the earliest epochs when the planet was still being reshaped by massive impacts to the relatively recent past, when bombardment rates had declined to near modern levels. Some scarps appear to be younger than 1 billion years. Some may be younger than 100 million years. On geological timescales, these are active features. Enterprise Rupes serves as a particularly striking example. This fault system stretches approximately 1,000 kilometers across Mercury's surface and displays vertical displacements of up to 3 kilometers, making it one of the largest known tectonic features in the solar system. The fault trace cuts across terrain of varying ages, demonstrating prolonged activity spanning billions of years. At 3 kilometers of throw, Enterprise Rupes has accommodated enormous crustal shortening, its western block thrust eastward over the adjacent surface like a massive tectonic wave frozen in stone. The Labat scarps are not the only contractional features on Mercury. Messenger also revealed networks of smaller ridges called wrinkle ridges that crisscross the smooth volcanic plains. These features form through compression as well, though at smaller scales than the Great Labat scarps. Wrinkle ridges are common on the Moon and Mars, where they formed primarily in response to loading by massive lava flows. On Mercury, they appear in the smooth plains but also in other terrains, suggesting that global contraction contributed to their formation alongside any local stresses from volcanic activity. Together, the lobate scarps and wrinkle ridges tell a story of a planet being squeezed from within. Mercury's crust has shortened by tens of kilometers to accommodate the shrinking core. The surface area of the planet has decreased measurably. If you could somehow peel Mercury's crust off and lay it flat, it would be too large to wrap around the present-day planet without overlap. The geological record preserves this excess surface area as thrust faults and ridges, the crumpled remnants of a time when Mercury was larger. This ongoing contraction connects to Mercury's thermal environment in ways that seem paradoxical at first. The planet closest to the Sun is cooling. The world that endures the most intense solar heating of any rocky planet is losing heat to space faster than it gains heat from the Sun. The resolution of this paradox lies in the distinction between surface temperature and interior temperature. Mercury's surface undergoes the most extreme temperature swings in the solar system, from roughly 430 degrees Celsius on the sunlit equator to negative 180 degrees Celsius in the permanently shadowed polar craters. These are surface phenomena, driven by the Sun's radiation and Mercury's lack of atmosphere. The interior of the planet operates on completely different physics. 4.5 billion years ago, Mercury's core was far hotter than today. The energy locked in that molten iron came from the gravitational collapse that formed the planet, from radioactive decay of elements like uranium, thorium, and potassium distributed throughout the interior, and from the release of latent heat during early crystallization. This primordial heat has been conducting outward ever since, passing through the mantle, reaching the surface, and radiating into space. The core's temperature has dropped by hundreds of degrees over the age of the solar system. The crystallizing inner core releases additional latent heat, but this merely slows the cooling rather than reversing it. Mercury's mantle, thin as it is, acts as a thermal insulator, slowing the rate at which core heat escapes. But the planet's small size works against this insulation. Mercury's surface-to-volume ratio is higher than Earth's, meaning heat can escape more efficiently relative to the total thermal energy stored within. The cooling is inexorable, driven by the fundamental thermodynamics of a small body embedded in cold space. The temperature swings at Mercury's surface arise from a different mechanism entirely. Mercury rotates slowly on its axis, completing one rotation every 58.6 Earth days. Its orbital period is 88 Earth days. The 3-2 resonance between these periods creates a solar day, the time from one noon to the next at any point on Mercury's surface of approximately 176 Earth days. For 88 Earth days, any given location experiences continuous sunlight, baking under the unfiltered glare of a sun that appears more than twice as large and delivers more than 6 times the radiation it provides at Earth. Then, for 88 Earth days, that same location experiences continuous darkness, its heat radiating away into the cosmic void with no atmosphere to retain warmth. The temperature range is staggering. Daytime temperatures at the subsolar point can exceed 430 degrees Celsius, hot enough to melt lead, zinc, and several other metals. At local noon on the equator, Mercury's surface is hotter than most kitchen ovens can reach. Nighttime temperatures plunge to negative 180 degrees Celsius, colder than anywhere on Earth's surface has ever been recorded. A single point on Mercury's surface can experience a temperature swing of more than 600 degrees Celsius over the course of one solar day. This thermal cycling imposes extraordinary stresses on surface materials. Rocks expand when heated and contract when cooled. The expansion and contraction coefficients of different minerals vary, meaning that a rock composed of multiple mineral species will experience internal stresses as its components expand and contract at different rates. Over hundreds of millions of cycles, these stresses contribute to the mechanical weathering of surface rocks, fracturing them along grain boundaries and creating the fine-grained regolith that blankets Mercury's surface. The regolith itself presents a striking dichotomy. Mercury's surface is among the darkest of the rocky planets, with an average reflectivity of only about 12%. The material is darker than asphalt, darker than most volcanic rocks on Earth, absorbing the vast majority of the sunlight that strikes it. Messenger spectra revealed that this darkness correlates with concentrations of carbon, likely delivered by micrometeorite and comet impacts over billions of years. The carbon may exist as graphite, mixed into the soil by countless impacts that vaporize, excavate, and redistribute surface materials across the globe. Yet despite this overall darkness, Mercury displays dramatic albedo variations. Fresh impact craters expose brighter material from beneath the surface, creating ray systems that extend hundreds of kilometers from young impact sites. These rays gradually darken over millions of years as space weathering processes alter the exposed material. The hollows, those peculiar bright depressions discovered by Messenger, stand out even more strikingly against the dark surrounding terrain, their floors and walls displaying the highest reflectivity found anywhere on Mercury's surface. The formation mechanism of hollows remains one of Mercury's most intriguing mysteries. These irregular depressions appear fresh by geological standards, with sharp edges unblunted by subsequent impacts and floors devoid of the small craters that would accumulate over long time periods. Their preferential occurrence on crater floors, central peaks, and other locations where subsurface material has been excavated suggests that some volatile substance lies just beneath Mercury's surface, sublimating away when exposed to the harsh space environment. But what volatile could survive in rocks that reach 430 degrees Celsius? Sulfur compounds represent the leading candidates. Sulfur has a relatively low sublimation temperature under vacuum conditions, and Messenger detected abundant sulfur in Mercury's surface materials. Under the specific pressure and temperature conditions of Mercury's surface, sulfur-bearing minerals might remain stable for billions of years while buried, only to sublimate rapidly when impact excavation brings them within reach of the vacuum and solar heating. The sublimation would remove material preferentially, creating the irregular depressions observed as hollows, while leaving behind the more refractory rock matrix. Alternative hypotheses invoke other volatile elements like chlorine or potassium, both detected by Messenger in Mercury's surface composition. Whatever the responsible compound, the existence of hollows indicates that Mercury's geology remains active in ways unrelated to the tectonic activity driven by core contraction. The planet is not merely shrinking, it is also losing material to space through some form of sublimation or thermal erosion that continues to reshape small-scale surface features. The volcanic history of Mercury adds another layer to this geological tapestry. Messenger revealed that smooth plains cover approximately 27% of Mercury's surface, and spectroscopic and morphological evidence indicates that many of these plains are volcanic in origin. Some plains fill ancient impact basins, much as mare basalts fill the basins on the near side of the Moon. Others occur in intercrater regions, suggesting extensive volcanic flooding beyond the basin-filling eruptions. The volcanic deposits are generally old, with most activity appearing to have concluded by roughly 3.5 billion years ago, but their extent indicates a period of prodigious magma production early in Mercury's history. The Caloris Basin contains particularly impressive volcanic plains. This enormous impact structure, roughly 550 kilometers in diameter, represents one of the largest impact basins in the solar system. The impact that created Caloris occurred approximately 3.9 billion years ago, during the late heavy bombardment that scarred every rocky body in the inner solar system. The energy released by this impact was sufficient to create antipodal disruption on the opposite side of Mercury, producing a region of hilly, chaotic terrain called weird terrain that defies simple explanation. Some models suggest seismic waves from the impact converged at the antipodal point, focusing their energy to disrupt the crust. Others propose ejecta from the impact travelled around the planet to accumulate at the antipode. The true mechanism remains debated. Within the Caloris Basin, volcanic flooding deposited smooth plains that partially buried the basin's interior structures. These lava flows smoothed the surface, erasing smaller craters and creating the relatively flat terrain visible today. Ghost craters, the spectral outlines of impact structures nearly drowned by lava, hint at the depth of volcanic material accumulated in the basin. The volcanism that flooded Caloris was not a single event but a prolonged episode spanning perhaps hundreds of millions of years. With multiple lava flows burying successively younger surfaces, the composition of Mercury's volcanic rocks differs from volcanic materials on other planets. Messenger's spectrometers found that Mercury's surface is surprisingly depleted in iron relative to the Moon and Mars. The lavas that erupted onto Mercury's surface contained less iron-bearing minerals than the basalts familiar from Earth, the Moon, or Mars. This iron depletion makes Mercury's volcanic rocks more similar to some unusual terrestrial rock types, such as the komatiites that erupted on early Earth, when mantle temperatures were higher and melting processes differed from those of modern volcanism. The low iron content connects to Mercury's anomalous overall composition. If the planet's core claimed an outsized share of the available iron during planetary formation, or during a giant impact that stripped the mantle, then the remaining silicate mantle would be depleted in iron. Melting of this iron-poor mantle would produce iron-poor magmas, explaining the volcanic compositions Messenger observed. The surface geology thus reflects the deep interior structure, connecting the lava flows visible in orbital images to the massive core thousands of kilometers below. Geological time on Mercury follows a sequence familiar from other heavily cratered bodies. The oldest surfaces preserve the scars of the late heavy bombardment, saturated with overlapping craters to the point where new impacts can only obliterate traces of older ones. These pre-Tolstoyan terrains record the chaotic early era, when debris left over from planet formation still swarmed through the inner solar system. The Tolstoyan and Calorian periods saw the formation of Mercury's largest surviving impact basins and the volcanic flooding that followed. The Mansurian and Kuiperian periods, named for younger impact craters, record the declining impact rate as the solar system gradually swept itself clean of collision hazards. The most recent Kuiperian surfaces preserve fresh ray systems and small craters that have not yet been erased by the slow rain of micrometeorites. Throughout this history, the lobate scarps have continued to form and grow. Some scarps cut ancient terrain, suggesting early formation. Others cut relatively young plains, demonstrating continued activity. The superposition relationships between scarps and craters provide a chronological framework, revealing that contraction-driven tectonics has operated continuously from Mercury's earliest eras to the geologically recent past. The persistence of scarp formation across billions of years raises a question that penetrates to the heart of planetary evolution. If Mercury's contraction resulted solely from the cooling of its primordial heat, simple thermal models predict that most shortening should have occurred early, when the planet was hottest and cooling most rapidly. Yet the geological evidence suggests ongoing activity, scarps cutting surfaces that formed well after the initial thermal spike had dissipated. Something else must be contributing to Mercury's continued shrinkage, some process that extends the contraction far beyond what simple cooling alone would predict. The answer lies in the crystallization of Mercury's inner core. Deep within the planet, at pressures exceeding those found anywhere on Earth, the liquid iron of the outer core is gradually solidifying. This crystallization releases energy in two forms. The first is latent heat, the thermal energy released when liquid transforms to solid, analogous to the warmth felt when water freezes. This latent heat helps maintain the thermal gradient that drives Mercury's weak magnetic field through dynamo action. The second form of energy release comes from the volume change accompanying solidification. Liquid iron occupies more space than solid iron at the same pressure. As the inner core grows, atom by atom, the newly solidified iron packs more efficiently than its liquid precursor. Each increment of core crystallization reduces the planet's total volume by a small but measurable amount. The mathematics of this process are striking. Iron contracts by approximately 2 to 3% when it solidifies under the pressure conditions present at Mercury's core mantle boundary. If Mercury's inner core has grown from nothing to its current estimated size of perhaps 1,000 to some 200 kilometres in radius over the past 4 billion years, this solidification alone could account for several kilometres of total radial contraction. Combined with thermal contraction of both the core and mantle, the models begin to approach the 7 to 14 kilometres of shortening that the Lebate scarps record. The planet is shrinking not merely because it is cooling, but because its heart is slowly crystallizing, turning from liquid to solid in a process that will continue for billions of years into the future. This ongoing core solidification connects Mercury's surface geology to its internal dynamics in a way that illuminates planetary evolution across the solar system. Earth's inner core is also growing through the same crystallization process, but Earth's larger size and higher internal temperatures mean this growth proceeds more slowly. Mercury, smaller and cooling faster, represents an advanced stage in the evolution that all rocky planets with iron cores will eventually experience. By studying Mercury's contraction, scientists gain insight into processes that will shape Earth's deep interior on timescales stretching billions of years into the future. The thermal environment at Mercury's surface provides another window into the planet's physical extremes. No world in the solar system experiences temperature swings as violent as those Mercury endures. At perihelion, when Mercury swings closest to the Sun, the subsolar point receives nearly 11 times the solar intensity that Earth experiences. Surface temperatures at local noon can reach 700 Kelvin, roughly 427 degrees Celsius or 800 degrees Fahrenheit. This is hot enough to melt lead, zinc, and tin. It approaches the melting point of aluminum. The rock itself glows faintly with thermal radiation at these temperatures, radiating heat into the vacuum of space. Yet Mercury rotates so slowly that its nights are interminable. The combination of the 59-day rotation period and 88-day orbital period produces a solar day, the time from one noon to the next, of approximately 176 Earth days. This means that any given point on Mercury's surface experiences 88 Earth days of continuous sunlight, followed by 88 Earth days of continuous darkness. During these long nights, with no atmosphere to retain heat, surface temperatures plummet. The same locations that broil at 700 Kelvin during the day can cool to 100 Kelvin at night, roughly negative 173 degrees Celsius or negative 280 degrees Fahrenheit. This is colder than any naturally occurring temperature on Earth, colder than liquid nitrogen, approaching the temperature of Saturn's moon Titan. The temperature difference between Mercury's day and night sides thus approaches 600 Kelvin. No other planetary surface in the solar system experiences such extreme thermal cycling. This 600-degree swing occurs repeatedly, twice per Mercury year, subjecting the surface rocks to thermal stresses that would shatter most terrestrial materials. The expansion and contraction accompanying these temperature changes creates a unique weathering environment. Rocks expand in the searing daytime heat, contract in the frigid nighttime cold, and gradually develop networks of microcracks that propagate with each thermal cycle. Over millions and billions of years, this thermal weathering contributes to the regolith formation that blankets Mercury's surface in a layer of fragmented and pulverized rock. The thermal extremes create another phenomenon that seems counterintuitive for the planet closest to the Sun. Mercury hosts water ice. This discovery, first suggested by Earth-based radar observations in 1991 and confirmed by MESSENGER 2 decades later, represents one of the most surprising findings in planetary science. The ice exists in permanently shadowed regions near Mercury's poles, in crater floors that never receive direct sunlight due to Mercury's nearly zero axial tilt. Mercury's rotation axis is tilted by only about 0.034 degrees relative to its orbital plane, essentially perpendicular to the ecliptic. This means the Sun never rises more than a few degrees above the horizon, as seen from Mercury's poles. The floors of deep craters at high latitudes remain in perpetual shadow, never illuminated by direct sunlight throughout Mercury's entire history. These permanently shadowed regions act as cold traps, maintaining temperatures below 100 Kelvin year-round despite Mercury's proximity to the Sun. Water molecules delivered by comet impacts or created by solar wind interactions with oxygen-bearing minerals can migrate across Mercury's surface until they encounter these cold traps. Once frozen into the shadowed crater floors, the water ice can persist for billions of years, protected from sublimation by the eternal darkness. Messenger's neutron spectrometer detected the hydrogen signature of water ice in Mercury's northern polar regions. The spacecraft's imaging systems captured photographs of the shadowed crater floors using light scattered from nearby sunlit terrain, revealing bright deposits consistent with exposed water ice. Some craters show the ice overlain by a darker layer of material, possibly organic compounds delivered by the same comets that brought the water. The total quantity of ice remains uncertain, but estimates suggest Mercury's polar cold traps could contain between 100 billion and 1 trillion metric tons of water ice. This is a small fraction of Earth's water budget, but represents a significant resource for any future human presence in the inner solar system. The existence of water ice on Mercury transforms our understanding of this scorched world. Here is a planet where the daytime surface can melt lead, yet water ice persists indefinitely in permanently shadowed refuges just a few hundred kilometres away. The contrast embodies the extremes that define Mercury's character. The same orbital and rotational geometry that produces the temperature extremes also creates the conditions for ice preservation. The planet's minimal axial tilt is not merely an astronomical curiosity, but a geological agent, sculpting the distribution of volatiles across Mercury's surface. The delivery mechanisms for Mercury's polar ice connect the planet to the broader history of the solar system. Comets, the icy remnants of the outer solar system, occasionally plunge sunward on trajectories that bring them into the inner solar system. Some strike Mercury, delivering water and organic compounds to its surface. The impacts that created Mercury's craters also helped stock its cold traps with ice. The water currently frozen at Mercury's poles may have originated in the outer solar system, beyond the orbit of Jupiter, carried inward by gravitational perturbations over millions of years. In this sense, Mercury's polar ice is a gift from the far reaches of the solar system, a connection between the innermost rocky world and the frozen domain of comets and trans-Neptunian objects. The regolith that blankets Mercury's surface records the cumulative effects of billions of years of bombardment. Like the Moon, Mercury lacks an atmosphere capable of shielding its surface from impacts. Every micrometeorite, every grain of cosmic dust, every boulder flung from asteroid collisions reaches Mercury's surface at full velocity. The continuous rain of impacts pulverizes the surface rocks, creating a layer of fragmented material called regolith that buries the underlying bedrock. Messenger's observations suggest Mercury's regolith is several meters thick in most locations, deeper in ancient, heavily cratered terrain, shallower on younger volcanic plains. The regolith itself undergoes a process called space weathering that alters its optical properties over time. Solar wind bombardment, ultraviolet radiation, and micrometeorite impacts combine to modify the surface minerals. Iron within the silicate minerals is reduced to nanometer-scale metallic particles that darken the surface and alter its spectral properties. This space weathering explains why Mercury's surface appears relatively dark, despite being composed of iron-poor silicate minerals that would appear bright if freshly exposed. The weathered regolith also develops a distinctive reddening in its spectral signature, shifting its reflectance toward longer wavelengths. These space weathering effects complicate the interpretation of Mercury's surface composition from orbital observations, requiring careful modelling to extract the underlying mineralogy from the altered spectra. The geological processes operating on Mercury today differ markedly from those on Earth. Without plate tectonics, there is no recycling of crustal material back into the mantle. Without an atmosphere, there is no wind erosion, no chemical weathering, no transport of sediment by flowing water. Without surface liquids, there are no rivers, lakes, or oceans to sculpt the landscape. The only active processes are impact cratering, the continued formation of lobate scarps as the planet contracts, and the relentless modification of the surface by space weathering. These processes operate slowly by human standards but inexorably over geological time. Yet Mercury is not entirely dead. The ongoing contraction implies that the interior remains active, that heat continues to flow outward, that the core continues to crystallize. The magnetic field, weak though it is, testifies to convective motions in the liquid outer core. Mercury represents a world in slow transition, gradually losing its internal heat, progressively solidifying its core, continuously shrinking as it ages. The planet we observe today is a snapshot of this evolution, frozen in geological time, waiting for future observations to reveal the next chapter of its story. Messenger transformed our understanding of Mercury, but its mission ended in 2015 when the spacecraft exhausted its fuel supply and crashed into Mercury's surface, creating a small crater that future visitors might someday identify. The spacecraft had orbited Mercury for 4 years, mapping the entire surface, measuring the composition of rocks and volatiles, probing the magnetic field and magnetosphere, detecting the planet's subtle wobble that revealed the liquid core. By any measure, Messenger was a spectacular success, rewriting the textbook on Mercury with almost every observation. Yet Messenger's data raised as many questions as it answered. The low iron content of Mercury's surface remained puzzling, difficult to reconcile with the standard models of planet formation. The hollows demanded explanation, their formation mechanism still incompletely understood. The magnetic field's offset from the planetary centre suggested asymmetries in core convection that existing models struggled to reproduce. The volcanic history, while better constrained than before, still contained gaps and uncertainties. The ongoing contraction, while clearly documented, required more precise measurements to fully characterise. Into this landscape of questions arrived Bepi Colombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. Launched in October 2018, Bepi Colombo is currently en route to Mercury, following a complex trajectory that uses gravitational assists from Earth, Venus and Mercury itself to gradually slow the spacecraft and insert it into Mercury orbit. The journey is arduous, requiring 7 years of travel and 9 planetary flybys to reach its destination. Bepi Colombo is scheduled to enter Mercury orbit in December 2025, beginning a science mission designed to answer the questions Messenger left unresolved. Bepi Colombo is actually 2 spacecraft travelling together. The Mercury Planetary Orbiter, built by the European Space Agency, will study Mercury's surface, interior and magnetic field. The Mercury Magnetospheric Orbiter, built by JAXA, will focus on Mercury's magnetosphere and its interaction with the solar wind. The 2 orbiters will separate upon arrival at Mercury, entering complementary orbits that maximise scientific return. This dual spacecraft architecture enables simultaneous measurements that a single orbiter could never achieve, allowing scientists to distinguish temporal changes from spatial variations in Mercury's magnetic environment. The flybys Bepi Colombo has already completed during its cruise to Mercury have provided tantalising glimpses of the planet. The spacecraft first encountered Mercury in October 2021, passing within 200 kilometres of the night side. Additional flybys in 2022, 2023, 2024, and planned for 2025 have progressively refined the trajectory while returning images and data that preview the scientific harvest to come. These flyby images, though brief snapshots compared to the sustained observations orbital science will provide, have already revealed surface features at resolutions exceeding Messenger's best images. Bepi Colombo carries 11 instruments on the European orbiter and 5 on the Japanese orbiter, a suite of sensors designed to address specific questions about Mercury's formation, evolution, and current state. Spectrometers operating across multiple wavelength ranges will map Mercury's surface composition in detail Messenger could not achieve. A laser altimeter will measure surface topography with meter-scale precision, revealing the subtle vertical displacements along Labarthe scarps and other tectonic features. Magnetometers on both spacecraft will probe Mercury's magnetic field from different vantage points, constraining the geometry of the dynamo generating the field deep within the core. The thermal infrared imaging spectrometer aboard Bepi Colombo will measure surface temperatures across Mercury with unprecedented precision, mapping the thermal environment from the scorching sub-solar point to the frigid, permanently shadowed craters. These measurements will constrain thermal inertia, a property that reveals the physical characteristics of surface materials. High thermal inertia indicates consolidated rock that absorbs and releases heat slowly. Low thermal inertia suggests loose, porous regolith that responds quickly to changing illumination. By mapping thermal inertia globally, Bepi Colombo will reveal variations in surface texture that orbital imaging alone cannot detect. The mission will also search for additional water ice deposits and other volatiles in Mercury's polar cold traps, While Messenger confirmed the presence of ice in northern polar craters, the southern pole remained less thoroughly explored due to the spacecraft's highly elliptical orbit, which brought it closest to the surface over the northern hemisphere. Bepi-Colombo's orbit will provide better coverage of the southern regions, potentially revealing additional ice deposits and constraining the total volatile inventory of the innermost planet. Understanding Mercury's volatile budget connects to fundamental questions about planetary formation. The standard models predict that Mercury should be essentially devoid of volatile elements, baked dry by its proximity to the young Sun. Yet, Messenger found evidence not only for water ice but for other volatile species including sulfur and potassium, at abundances higher than expected. If Mercury retained volatiles despite its harsh environment, or if volatiles were delivered after the planet formed, the implications extend to our understanding of how terrestrial planets acquire and retain the ingredients for life. Bepi-Colombo will also probe Mercury's interior through gravity measurements and rotational dynamics. As the spacecraft orbits Mercury, tiny variations in its velocity reveal subtle changes in the planet's gravitational field. These gravity anomalies map mass concentrations beneath the surface, the dense cores of ancient impact basins, the lighter material of volcanic plains, the variations in crustal thickness that record the planet's thermal and tectonic history. By combining gravity data with topography, scientists will model Mercury's internal structure in 3 dimensions, constraining the size and state of the core with precision that previous measurements could not achieve. The rotational state of Mercury provides another probe of the interior. The planet does not rotate perfectly smoothly, but exhibits tiny oscillations called librations, wobbles in its orientation caused by the gravitational pull of the Sun on Mercury's non-spherical figure. The amplitude of these librations depends on the coupling between Mercury's mantle and core. If the core were solid, the entire planet would wobble as a single unit. Because the core is partially liquid, the mantle and core wobble somewhat independently, producing libration amplitudes that reveal the core's state. Messenger's measurements of these librations provided the first direct evidence for Mercury's liquid outer core. Bepi-Colombo will refine these measurements, potentially detecting changes in libration amplitude that would indicate ongoing core evolution. The mission's magnetospheric observations will address the puzzle of Mercury's offset magnetic field. Why does the field appear centered roughly 480 kilometers north of the planet's geometric center? One hypothesis suggests that heat flow from the core is asymmetric, with more heat escaping from the southern hemisphere and driving more vigorous convection in the northern outer core. This asymmetric convection would generate an asymmetric magnetic field, shifted toward the more active northern hemisphere. Another hypothesis invokes feedback between the magnetic field and the crystallizing inner core, with field geometry influencing where solidification occurs and vice versa. Bepi-Colombo's dual orbiters, measuring the field simultaneously from different locations, will map the field geometry in unprecedented detail, testing these hypotheses against observation. The science returned from Bepi-Colombo will take years to fully analyze. Mercury's mysteries will not yield to a single flyby or even a single orbital mission. Each answered question reveals deeper questions beneath. The planet closest to the Sun guards its secrets behind veils of sunlight and heat, revealing them only to those with the patience to ask and the technology to listen. Yet the trajectory of understanding points clearly forward, from the earliest telescopic observations through Mariner 10's fleeting glimpses, from Messenger's comprehensive mapping to Bepi-Colombo's targeted investigations. Each mission has rewritten Mercury's story. The planet that seemed so simple, so featureless, so easily dismissed as a larger version of the Moon, has revealed depths that early observers could not have imagined. A world with a magnetic field generated by dynamo action in a partially liquid core. A world still contracting as that core crystallizes, wrinkling its surface with fault scarps visible from orbit. A world with water ice in permanently shadowed craters despite surface temperatures that exceed the melting point of lead. A world with mysterious hollows and ghost craters and chaotic terrain that record impacts and volcanism and processes not yet fully understood. Mercury is not a footnote, it is a laboratory. The smallest and innermost terrestrial planet occupies a unique position in the solar system, experiencing conditions found nowhere else. Its proximity to the Sun exposes it to radiation intensities that no other planet endures. Its slow rotation creates temperature extremes that no other surface matches. Its oversized core preserves information about planetary formation that larger, more thoroughly processed worlds have lost. Mercury is not boring, because we have learned everything worth knowing. Mercury seemed boring because we had not yet developed the tools to ask the right questions. The questions we now ask of Mercury require us to descend beneath the surface, to journey through kilometres of rock and metal into a realm no spacecraft can directly observe. We must reconstruct the deep interior from surface clues, from gravity anomalies and magnetic field variations, and the subtle wobble of a planet responding to forces that act upon its hidden mass. This reconstruction reveals a world unlike any other in our solar system, a planet that is, in a very real sense, mostly core. When planetary scientists describe Mercury's internal structure, they begin with a fact so striking that it bears repetition, until it becomes intuitive rather than merely surprising. Mercury's iron core occupies roughly 85% of the planet's radius. Not 85% of its volume, though that figure is impressive enough, but 85% of the distance from centre to surface. Imagine standing at Mercury's equator and drilling straight down toward the centre. You would pass through a thin veneer of silicate crust, perhaps 30 to 40 kilometres thick in some regions, thinner in others. Beneath the crust lies a mantle of silicate rock, denser than the crust, but still composed of the rocky minerals that form the bulk of Earth's interior. On Earth, this mantle extends roughly 2,900 kilometres before giving way to the outer core. On Mercury, the mantle ends after perhaps 400 kilometres. The remaining 1,800 kilometres to the centre is iron. Pure, dense, heavy iron, mixed with lighter elements like sulphur and silicon, but dominated by the metallic element that makes Mercury unique among terrestrial worlds. This proportion defies the compositional models that describe planetary formation in the inner solar system. Standard accretion scenarios predict that Mercury should have a core-to-planet ratio similar to Earth or Venus or Mars, that the iron and silicate components should have accreted in roughly similar proportions across the terrestrial planet zone. Mercury's anomalous composition demands explanation, and the explanations reveal as much about planetary violence as they do about Mercury itself. The giant impact hypothesis proposes that Mercury was once larger, perhaps twice its current mass, with a conventional core-to-mantle ratio. Early in solar system history, within the first 100 million years when the inner planets were still assembling from the debris of the protoplanetary disk, a massive object struck the proto-Mercury with catastrophic force. The collision stripped away most of the silicate mantle, blasting it into space as vapour and debris that scattered across the inner solar system. What remained was the original core plus a thin veneer of surviving mantle material, a planet reduced to its dense metallic heart. This hypothesis explains Mercury's anomalous density elegantly. The iron core was always proportional to the original planet's mass. The impact simply removed the surrounding rock, leaving the core exposed beneath a thin skin of surviving silicates. Alternative hypotheses invoke the extreme conditions of Mercury's formation zone rather than later catastrophe. In the high-temperature inner disk where Mercury accreted, silicate minerals would have remained solid while iron-rich metal condensed from the gas phase. If the dust-to-gas ratio in this region favoured metal over silicates, Mercury could have formed iron-rich from the beginning. This scenario requires specific disk conditions, but avoids the coincidence of a giant impact striking at just the right angle and velocity to strip mantle, without destroying the planet entirely. A third hypothesis proposes that early solar radiation blasted away Mercury's outer layers through vaporization. The young sun was more luminous in its first few million years, and Mercury orbited through a region where rock vaporizing temperatures were common. Repeated cycles of heating and cooling could have preferentially removed lighter silicate material, while heavier iron remained gravitationally bound. This process would have gradually enriched Mercury in iron over millions of years, a slow cooking rather than a sudden blow. Current evidence cannot definitively distinguish among these hypotheses. Each makes predictions about Mercury's bulk composition that Bepi Colombo and future missions may test. The giant impact scenario predicts certain volatile depletions that a hot formation environment might not produce. The vaporization model predicts compositional gradients that impact stripping might not create. For now, Mercury's oversized core remains a puzzle with multiple plausible solutions and no confirmed answer. What we can say with confidence is that this massive core dominates Mercury's current behaviour. The core is not a static lump of metal sitting inert beneath the mantle. It is a dynamic system, actively convecting, partially liquid, crystallizing at its center, generating the magnetic field that makes Mercury the most magnetically active small rocky body we know. Understanding Mercury requires understanding its core, and understanding its core requires understanding the processes that have operated within it for more than 4 billion years. The liquid outer core that generates Mercury's magnetic field consists primarily of iron, alloyed with lighter elements. These lighter elements are crucial. Pure iron at Mercury's core pressures would likely be entirely solid. The addition of elements like sulfur, silicon, oxygen, or carbon depresses the melting point, allowing a substantial fraction of the core to remain liquid at temperatures that would otherwise drive complete solidification. The precise composition of these light elements remains uncertain, but their presence is required to explain Mercury's liquid outer core and active dynamo. At the very centre of the planet lies the solid inner core, a region of crystallized iron that grows slowly as the planet cools. This growth is not rapid by human standards. Estimates suggest the inner core may expand by only a fraction of a millimetre per year, a rate that would require millions of years to produce changes measurable by any conceivable instrument. Yet over geological time, this gradual crystallization drives the most dramatic ongoing transformation of Mercury's structure. As the inner core grows, it releases latent heat that powers convection in the overlying liquid. It also rejects light elements that float upward into the outer core, driving chemical convection that supplements thermal convection. Both processes generate the fluid motion that creates and sustains Mercury's magnetic field. The temperature at Mercury's centre likely exceeds 2000 degrees Celsius, perhaps approaching 2500 degrees. This seems impossibly hot for a world that has been cooling for 4.5 billion years. But large planetary bodies lose heat slowly. The rock and metal that compose Mercury are poor thermal conductors. Heat generated during formation and by radioactive decay takes eons to reach the surface and radiate into space. Earth's core remains hotter than Mercury's despite Earth's greater size, precisely because Earth has even more thermal inertia. Mercury's smaller mass means it has cooled faster, but not fast enough to extinguish the thermal reservoir at its heart. This ongoing cooling manifests at Mercury's surface in one of the most dramatic geological phenomena we can observe from orbit. The planet is shrinking, not rapidly, not catastrophically, but steadily and measurably. As the core cools, the iron within contracts. As the iron contracts, the entire planet reduces in diameter. This reduction has accumulated over billions of years, producing surface features that record the compression in stone. The evidence for contraction covers Mercury's entire surface. Thrust faults, structures where one section of crust has been shoved over another, snake across the planet in sinuous arcs that can extend for hundreds of kilometres. Planetary scientists call these features lobate scarps for their curved, lobe-like shapes. They are not subtle features requiring careful measurement to detect. The largest lobate scarps on Mercury tower over 1 kilometre high and stretch more than 500 kilometres across the surface. They are among the longest fault systems on any terrestrial planet, visible in orbital imagery as dramatic cliffs that cut across craters, through volcanic plains, over everything in their path. The formation mechanism of lobate scarps is straightforward in principle. As the core contracts, the overlying mantle and crust must accommodate the reduced volume. But solid rock cannot contract uniformly like cooling metal. The stresses build until the rock fails, breaking along thrust faults that push one section up and over another. Each lobate scarp represents a moment of failure, a release of accumulated strain that had built over perhaps millions of years. The total length of lobate scarps mapped by Messenger suggests that Mercury has contracted by approximately 7 kilometres in radius since the end of heavy bombardment, roughly 4 billion years ago. 7 kilometres of radial shrinkage may sound modest, but it represents an enormous amount of crustal compression, enough to produce the fault systems that now crisscross the planet. Recent analyses have revealed that Mercury's contraction is not uniform across the surface. Some regions show more intense faulting than others, suggesting that crustal thickness variations or regional heat, flow differences influence where strain accumulates. Some lobate scarps appear fresher than others, their edges sharper, their relief less degraded by small impacts. These fresh-appearing scarps may indicate that contraction-driven faulting continues today. that Mercury remains tectonically active in a mode quite different from Earth's plate tectonics, but active nonetheless. The implications of ongoing contraction extend beyond surface geology. A shrinking planet must adjust its moment of inertia, the distribution of mass around its rotation axis. As Mercury contracts, its moment of inertia decreases slightly, and conservation of angular momentum requires the rotation rate to increase marginally. These effects are far too small to detect with current technology, but they represent the deep coupling between core processes and planetary behaviour that makes Mercury such a valuable laboratory. The lobate scarps are not the only tectonic features that record Mercury's thermal history. Wrinkle ridges, lower and more subdued than lobate scarps, mark regions of compression within volcanic plains. Extensional features, including graben and troughs, record periods when local stresses became tensional rather than compressional. The interplay of global contraction and regional stress variations has created a tectonic tapestry that planetary scientists are still learning to read. Each ridge and scarp and graben tells part of the story, and combining them reveals the thermal and mechanical evolution of a world that refuses to sit quietly. The surface temperature regime of Mercury adds another dimension to its geological story. No other terrestrial planet experiences temperature swings so extreme across such a regular cycle. When Mercury's day side faces the Sun, surface temperatures can exceed 430 degrees Celsius, hot enough to melt lead, hot enough that zinc and other relatively low melting point metals would flow like water. When the same region rotates into darkness, temperatures plummet to minus 180 degrees Celsius, cold enough to freeze carbon dioxide if any were present, cold enough that most materials become brittle and fracture-prone. This thermal cycling occurs slowly because of Mercury's 176-day solar day. A point on Mercury's equator experiences more than 88 Earth days of continuous heating as the Sun crawls across the sky, followed by 88 Earth days of continuous cooling in the long night. The surface rocks endure this punishment repeatedly, expanding and contracting with each cycle, accumulating thermal fatigue that may contribute to regolith production, and surface gardening over geological time. The subsurface temperature profile differs dramatically from the surface. Solar heating penetrates only the uppermost few centimetres of rock. Below this thermal skin, temperatures remain relatively constant, controlled by the slow leak of internal heat, rather than the rapid cycling of sunlight. At a depth of roughly 1 metre, the day-night temperature swings diminish to negligible levels. Mercury's interior lives in a different thermal world than its surface, insulated from the solar furnace that dominates the landscape above. This thermal dichotomy creates opportunities for survival in hostile conditions. Water ice, impossible on Mercury's sunlit surfaces, can persist indefinitely in polar craters, where permanent shadow maintains temperatures below minus 170 degrees Celsius. The radar Bright deposits discovered in these shadowed regions likely represent ice that has accumulated over billions of years, delivered by comet impacts and migrating through Mercury's tenuous exosphere to cold traps where sublimation cannot occur. These ice deposits challenge simple narratives about the solar system's thermal structure, demonstrating that proximity to the Sun does not preclude the presence of water ice when geometry and shadow create appropriate conditions. The hollows discovered by Messenger add another layer of complexity to Mercury's surface processes. These irregular depressions, found primarily in crater floors and central peaks, appear as bright, fresh-looking features with halos of reflective material around their margins. They are young, geologically speaking, showing no superimposed craters and maintaining crisp edges that would degrade quickly under Mercury's steady rain of micrometeorites. Some planetary scientists suspect that hollows are actively forming today, that whatever process creates them continues to operate in the present geological era. The leading hypothesis for hollow formation invokes sublimation of volatile materials exposed by impact cratering. When an impact excavates material from depth, it may bring to the surface compounds that are unstable under Mercury's extreme thermal conditions. These volatiles, perhaps sulfur compounds or other low sublimation point materials, would gradually escape into space, leaving behind the depressions we observe as hollows. The bright halos around hollows would then represent either the escaping volatile material or residual concentrations of reflective compounds that have not yet sublimated. This hypothesis requires that Mercury's interior contain volatile materials in greater abundance than traditional models predicted. A world so close to the Sun, experiencing such intense heating during its formation, should not retain significant volatiles in its crust. Yet the hollows suggest otherwise. Perhaps Mercury formed from materials already depleted in some volatiles, but not all. Perhaps volatiles were delivered after formation by cometary impacts and incorporated into the crust through burial and gardening. Perhaps the high-temperature formation scenarios are incorrect, and Mercury accumulated significant volatile-bearing material despite its proximity to the Sun. Each possibility rewrites some portion of Mercury's history, and by extension, the history of the inner solar system. The volcanic plains that cover much of Mercury's surface tell yet another story of the planet's thermal evolution. Unlike Earth's volcanic activity, which continues today at spreading centres and subduction zones, Mercury's volcanism appears to have ended roughly 3.5 billion years ago. The volcanic plains show no fresh lava flows, no volcanic constructs lacking impact craters, no evidence for recent eruption. The internal heat that once drove magma to the surface no longer produces sufficient melting to sustain volcanism. This cessation of volcanism reflects the same cooling that drives Mercury's contraction. As the interior cooled, the zone of partial melting in the upper mantle contracted and eventually disappeared. Without a melting zone, there is no magma, and without magma, there is no volcanism. The transition from volcanic activity to tectonic quiescence marks a fundamental shift in Mercury's geological character, a shift that Earth has not yet experienced but eventually will. The timing of this transition contains information about Mercury's thermal evolution that constrains models of interior dynamics. If volcanism ended earlier than expected, the planet may have cooled faster than predicted, perhaps because its mantle is more thermally conductive than estimated, or because its heat production from radioactive decay was lower. If volcanism persisted longer than expected, the opposite conclusions follow. Messenger's crater counts on volcanic plains provide the age estimates, and Bepi Colombo's measurements will refine them, but the story they tell remains one of a world that exhausted its volcanic potential long before terrestrial volcanism reached its current state. The interplay between Mercury's volcanic history and its tectonic history reveals a complex thermal evolution. During the period of active volcanism, roughly 4 billion to 3.5 billion years ago, lava flows filled impact basins and created the smooth plains that cover much of the northern hemisphere. These flows were not gentle eruptions, but massive outpourings that could resurface entire regions in geological instants. The Caloris Basin, one of the largest impact structures in the solar system, contains volcanic fill measuring kilometres thick in places, enough lava to have required tremendous heat flow from the interior. Even as volcanism waned, contraction continued. The lobate scarps that cut through volcanic plains demonstrate that thrust faulting post-dated the final lava flows. Some scarps appear to have formed relatively recently within the last few 100 million years, suggesting that contraction-driven faulting may persist into the present. This ongoing deformation makes Mercury one of the most tectonically active small bodies in the solar system, a designation that would surprise anyone who still thinks of it as a dead world. The mysteries multiply rather than diminish as measurements improve. Mercury's surface composition, mapped by Messenger's spectrometers, reveals surprisingly low iron content in the silicate crust despite the iron-rich core beneath. This iron depletion challenges formation models and suggests chemical processes that preferentially extracted iron from the mantle during differentiation. The planet's colour variations visible in enhanced imagery correlate with compositional differences that may trace volcanic source regions or impact excavated material from varying depths. The radar-bright deposits in polar craters may include volatiles beyond water ice, potentially organics or sulfur compounds that complicate the simple picture of frozen water in shadow. Bepi Colombo will address many of these mysteries directly, but each answer will likely generate new questions. This is the nature of planetary exploration. Ignorance breeds simplicity, and knowledge breeds complexity. Mercury seemed boring when we knew almost nothing about it. Mercury became fascinating when our ignorance lifted just enough to reveal how much we did not understand. The timeline stretches forward from here. Bepi Colombo's orbital operations began in late 2025 and will continue through at least 2028, with potential mission extensions if the spacecraft remains healthy. Data collected during these years will require additional years to fully analyse. Some discoveries will come quickly, announced in press releases and published in high-profile journals within months of observation. Others will emerge slowly, requiring years of careful analysis and comparison with existing datasets before their significance becomes clear. The Mercury science community is small compared to Mars or the Moon, but its members are dedicated to extracting every possible insight from the precious data that distant spacecraft provide. Future missions beyond Bepi-Colombo remain speculative but tantalizing. A Mercury lander would revolutionize our understanding of surface processes, providing direct measurements of composition, mineralogy, and seismic activity that orbital observations cannot achieve. The technical challenges are immense. Landing on a world with surface temperatures exceeding 400 degrees Celsius requires thermal protection systems that push the boundaries of materials science. Operating in such conditions for more than a few hours demands cooling systems or heat-tolerant electronics that do not yet exist. Yet engineers have solved similarly daunting problems before. The Soviet Venera landers survived on Venus's 460-degree surface long enough to return data. A Mercury lander might someday accomplish comparable feats. Human exploration of Mercury remains a distant prospect, likely centuries away if it occurs at all. The radiation environment, the temperature extremes, the difficulty of establishing any sustainable presence so close to the Sun all argue against crewed missions for the foreseeable future. Mercury will remain a world explored by robotic proxy, seen through the electronic eyes of spacecraft that can endure conditions no human body would survive. Yet the knowledge gained from robotic exploration extends human understanding across the solar system and beyond. Mercury is not merely one world among many. It occupies a unique position in parameter space, the extremes of temperature, radiation, and solar proximity that no other terrestrial planet matches. Understanding Mercury therefore illuminates possibilities that exist nowhere else in our cosmic neighbourhood. When scientists study Mercury's response to solar wind, they observe plasma physics operating under conditions more extreme than any laboratory on Earth can replicate. When they measure Mercury's surface temperatures across day and night, they document thermal cycling that tests materials science models at their limits. When they track the planet's subtle orbital motions, they probe space-time geometry in ways that complement but cannot be replaced by observations made elsewhere. Mercury is a natural laboratory whose experimental conditions the universe has set, and which we can only observe, never recreate. The lessons extend far beyond Mercury itself. Exoplanet surveys have discovered thousands of worlds orbiting other stars, and a surprising fraction of these orbit closer to their parent stars than Mercury orbits the Sun. These so-called hot super-Earths and warm Neptunes experience conditions that make Mercury's environment seem mild by comparison. Some orbit so close that their rocky surfaces might flow like molten glass. Their atmospheres stripped away by stellar radiation that dwarfs anything Mercury endures. Others may retain thick atmospheres that trap heat in runaway greenhouse effects that would make Venus jealous. Understanding how Mercury works, how its magnetic field protects what little atmosphere it has, how its surface responds to extreme thermal stress, how its interior evolves under intense tidal and thermal forcing, provides templates for understanding these distant worlds we will never visit. The connection runs deeper still. Mercury's formation and early history constrain models of how the entire inner solar system assembled. The excess iron that defines Mercury's density requires explanation, and that explanation must be consistent with the compositions of Venus, Earth, and Mars. If Mercury lost its mantle in a giant impact, the debris had to go somewhere. Some might have been swept up by other bodies. Some might have been scattered into the Sun. The total mass budget of the inner solar system must account for Mercury's anomaly. When planetary scientists construct numerical simulations of solar system formation, they tune their models to reproduce all 4 terrestrial planets simultaneously. Mercury provides the extreme test case, the outlier that challenges models tuned to reproduce the more moderate conditions of Earth and Mars. Any model that fails to produce something like Mercury probably misses important physics. This broader context elevates Mercury from curiosity to keystone. The innermost planet is not merely interesting in itself, but essential for understanding planetary systems in general. The ongoing observations, the data flowing back from Bepi-Colombo's instruments, the careful measurements of contraction and magnetic field strength and surface composition all contribute to a scientific enterprise larger than any single world. Mercury participates in the grand project of understanding how planets form, how they evolve, and what determines whether they become hospitable or hostile to life. The hostility of Mercury itself is absolute. No form of life we can imagine would survive on its surface for more than fractions of a second. The radiation, the temperature extremes, the complete absence of atmospheric protection all combine to create an environment more lethal than the vacuum of deep space in some respects. Even the permanently shadowed craters that harbour ice exist at temperatures so low that most terrestrial organisms would be killed instantly by cold rather than heat. Mercury is a world defined by extremes, and those extremes exclude the soft chemistry of biology as thoroughly as the interior of a fusion reactor would. Yet the water ice in those craters tells a story about the delivery of volatiles throughout the inner solar system, a process that may have seeded Earth with the oceans that life eventually emerged from. Mercury's lifelessness contributes to our understanding of life's origins elsewhere. The philosophical weight of Mercury has shifted dramatically over the centuries. Ancient astronomers saw Hermes as the swift messenger, a mere point of light that traced the fastest apparent path across their sky. Telescopic observers reduced that mythological figure to a heavily cratered sphere, apparently static and geologically dead. Modern spacecraft have revealed something far more dynamic, a world still contracting, still producing earthquakes, still interacting with the solar wind in complex ways that change from moment to moment. The scientific image has grown richer while the romantic image has faded. We no longer tell stories about the messenger of the gods racing across the heavens. We instead tell stories about iron cores and magnetic reconnection events, about Labat scarps and polar volatiles. The new stories are stranger than mythology, because they are constrained by what is actually true. What is actually true about Mercury continues to unfold as observations accumulate. Each orbit of Bepi Colombo adds to the dataset. Each pass over the planet's varied terrain reveals new details that demand explanation. The rhythm of discovery follows the rhythm of orbital mechanics, regular passes at predictable intervals that build comprehensive global coverage over months and years. Scientists on Earth receive the data, process it through software pipelines designed to extract meaningful signals from noisy measurements, and then spend years attempting to understand what those signals mean. The process is slow by human standards, achingly slow for researchers who devoted their careers to Mercury science, and may not live to see all their questions answered. Yet it is fast by geological standards, fast by the standards of a planet that has existed for 4.5 billion years and will continue to exist for billions more. Mercury's future stretches forward into a time so distant that human civilization, if it survives, will have changed beyond recognition. The sun will gradually brighten over the coming billions of years, and Mercury will receive ever more intense radiation. The increased heating will drive continued cooling of the core through enhanced heat loss from the surface, potentially strengthening the magnetic field before eventually causing it to fade as the core fully solidifies. The contraction that has already shrunk the planet by several kilometres will continue until the thermal contraction of the core ceases, a process that might take another billion years or more. The Lobat scarps will continue to grow, cutting through older features and creating new ones until the planet reaches thermal equilibrium with its environment. The ice in polar craters will be slowly depleted by impacts and solar winds sputtering unless replenished by continued comet and asteroid bombardment. Eventually, approximately 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core and begin expanding into a red giant. Mercury's fate during this phase is uncertain. Some models suggest the planet will be engulfed by the expanding solar envelope and spiral inward to destruction. Others suggest Mercury's orbit might expand as the Sun loses mass, potentially allowing the planet to survive the red giant phase as a scorched cinder orbiting a white dwarf remnant. The uncertainty reflects our incomplete understanding of stellar mass loss and tidal interactions during the red giant phase, problems that remain active areas of astrophysical research. Mercury's ultimate fate may not be determined for decades as computational models improve and observations of other stellar systems constrain the relevant physics. For now, Mercury exists in a kind of intermediate state, neither as pristine as it was 4 billion years ago, nor as transformed as it will be billions of years hence. The planet we observe today is a snapshot in a very long movie, a frame from a film that began with the violent birth of the solar system and will end only when the Sun itself dies. Understanding that snapshot requires understanding the frames that came before, the processes that shaped the world into its current form. It also requires acknowledging that the movie continues, that Mercury is changing even now, that the planet our grandchildren study will be subtly different from the planet we study today. The changes are small by human standards. The contraction might amount to fractions of a millimetre per year, far too small to detect directly. The magnetic field might strengthen or weaken by tiny amounts that require decades of observation to measure confidently. The ice deposits might shrink by layers of molecules too thin to resolve from orbit. Yet these imperceptible changes, summed over geological time, produce dramatic transformations. The Mercury that existed 1 billion years ago was measurably larger, measurably different in magnetic field strength, measurably different in surface features from the Mercury that exists today. The Mercury that will exist 1 billion years from now will be different again. The planet is alive in a geological sense, still evolving, still responding to the heat flowing from its core and the radiation pouring from its star. This dynamism contradicts the common perception of rocky planets as static objects, geologically dead after their primordial heat dissipated. Mercury proves that small rocky worlds can maintain geological activity for billions of years under the right conditions. The large iron core that makes Mercury dense also makes it tectonically active, providing the thermal engine that drives contraction. The weak magnetic field that seems insignificant compared to Earth's nonetheless shapes the planet's interaction with the space environment in ways that affect atmospheric composition and surface weathering. Mercury is not the inert ball of rock that simplified diagrams suggest. It is a complex system with internal dynamics that connect to external processes through multiple pathways. The external processes are themselves more complex than early observations suggested. The solar wind does not simply blast Mercury's surface uniformly. It interacts with the magnetic field to create regions of enhanced and reduced particle bombardment. It drives chemical reactions that liberate atoms from surface minerals, creating the tenuous exosphere that changes in composition from day to night and from perihelion to aphelion. It deposits particles from the sun onto the surface, mixing solar material with Mercury's native rocks in ways that affect spectral observations. The space environment is not merely a hostile backdrop against which Mercury exists, but an active participant in the planet's ongoing evolution. The interplay between internal and external processes creates feedback loops that scientists are only beginning to understand. The magnetic field generated by the core affects how the solar wind reaches the surface. The solar wind's impact on the surface affects the exosphere composition. The exosphere affects how radiation reaches the surface. The radiation affects surface chemistry and potentially the thermal budget. These connections mean that understanding any single aspect of Mercury requires understanding all the others. The planet is not a collection of independent phenomena, but an integrated system whose components influence each other through subtle and not so subtle mechanisms. Bepi Colombo's dual spacecraft approach directly addresses this systemic complexity. One spacecraft orbits close to the planet, studying surface and interior processes. The other orbits higher, studying the magnetic field and space environment. The two spacecraft pass through different regions of the Mercury system at different times, providing simultaneous measurements that reveal correlations invisible to any single observer. When the magnetometer on one spacecraft detects a magnetic reconnection event, scientists can check whether the spectrometers on the other spacecraft see corresponding changes in exosphere composition. When surface temperature measurements show dramatic changes at the day-night boundary, scientists can examine whether magnetic field structures change at the same locations. This coordinated approach enables science that no previous Mercury mission could achieve. The scientific coordination extends beyond the spacecraft to the international teams that analyze the data. Researchers from Japan, Europe, and partner nations share expertise in planetary geology, magnetospheric physics, spectroscopy, and mission operations. They meet at conferences, collaborate on papers, and engage in the sometimes contentious debates that characterize healthy scientific communities. The disagreements are productive. When one team's interpretation conflicts with another's, both are forced to examine their assumptions, seek additional evidence, and refine their models. Mercury science advances through this dialectical process, with competing hypotheses gradually resolved through the accumulation of data and the refinement of analysis techniques. The data itself represents a triumph of engineering over adversity. Every measurement Bepi Colombo returns required solving technical problems that would have been insurmountable a few decades ago. The heat shields that protect the spacecraft from solar radiation draw on materials science advances that emerge from the aerospace industry and academic research laboratories. The ion engines that propelled the spacecraft through the complex trajectory required years of development and testing. The scientific instruments pack capabilities that would have filled entire spacecraft a generation ago into compact packages that share limited power and data bandwidth. Each number in the scientific datasets represents the endpoint of a chain of engineering decisions, hardware fabrications, software implementations, and mission operations that stretched across decades and continents. The human effort behind those numbers is easy to forget when examining scientific results. A paper reporting Mercury's contraction rate does not describe the sleepless nights of engineers monitoring critical spacecraft maneuvers, the frustrating debugging sessions when software behaved unexpectedly, the anxious waiting during communication blackouts when the spacecraft was behind the sun. Yet those human experiences are as much a part of Mercury science as the planetary processes being studied. The knowledge we gain about Mercury is not generated automatically by instruments. It is constructed by communities of people who dedicate careers to understanding a world they will never touch. Their dedication deserves recognition even when scientific papers and press releases focus on results rather than process. The results, when they come, often surprise everyone. Mercury has defied expectations at nearly every turn. It was not supposed to have a global magnetic field, and it does. It was not supposed to have volatile rich deposits at its poles, and it does. It was not supposed to be tectonically active, and it is. Each surprise forced scientists to revise their models, to abandon assumptions that had seemed reasonable, to embrace explanations that had seemed unlikely. The scientific process worked as it should, updating beliefs in response to evidence rather than clinging to prior expectations despite contradictory data. Mercury humbled the scientists who studied it, rewarding their humility with insights that static expectations would have precluded. The humility extends to acknowledging what remains unknown. For all the advances of Messenger and Bepi Colombo, fundamental questions about Mercury persist. The origin of the planet's extreme density remains debated, with no single explanation commanding universal assent. The structure and state of the inner core are poorly constrained, depending on assumptions about thermal history that observations cannot directly test. The age and origin of the polar volatile deposits are uncertain, with competing hypotheses pointing to ancient comet impacts, ongoing delivery from the solar wind, or volcanic outgassing that has long since ceased. The rate and timing of future contraction depend on core properties that current measurements cannot resolve. Each answered question reveals additional questions hiding behind it, a fractal pattern of inquiry that extends to whatever depth scientists choose to explore. This endless depth is the true nature of scientific investigation. Mercury is not a puzzle with a finite number of pieces that might someday be completed. It is a world, and worlds contain infinite detail at every scale. The closer scientists look, the more they see. The more they understand, the more they realize how much they do not understand. The process has no end point, no final state of complete knowledge. There is only the ongoing endeavour, the gradual accumulation of the understanding that makes future investigators more capable than their predecessors, while leaving them equally aware of their own limitations. Mercury embodies this humbling reality more clearly than Earth or Mars, because Mercury is strange in ways that challenge assumptions. Studying Earth, scientists must constantly disentangle local familiarity from universal processes, recognizing when their intuitions built on terrestrial experience mislead them about planetary phenomena in general. Studying Mercury, the strangeness is impossible to ignore. The 59-day rotation period that creates days longer than years, the temperatures that span 600 degrees Celsius, the iron core that dominates the planetary volume, the magnetic field that barely deflects the solar wind. All force scientists to reason carefully rather than rely on intuition. Mercury does not let them coast on assumptions. It demands rigorous thinking and rewards that thinking with insights that transfer to other worlds and other problems. The insights already gained from Mercury have influenced fields far from planetary science. The solar-wind interaction, studies contribute to space weather prediction that protects satellites and power grids at Earth. The materials science research driven by spacecraft thermal protection needs has applications in industrial furnaces and aerospace propulsion. The orbital mechanics expertise developed for Mercury missions enables navigation techniques used throughout the solar system. The unexpected connections between basic research and practical applications justify scientific exploration beyond any single mission's immediate goals. Mercury science, pursued for its own sake by researchers fascinated by an extreme world, generates knowledge that diffuses through the technological economy in ways no one can fully predict. The economic argument for Mercury exploration is weak if measured in immediate returns, but the history of science demonstrates repeatedly that basic research generates benefits far exceeding the investment required to produce it. The electromagnetic theory developed by Maxwell and Faraday enabled the electrical industry that transformed civilization. The quantum mechanics developed by Bohr and Heisenberg enabled the semiconductor industry that created the information age. The planetary science developed by studying Mercury will enable applications that we cannot yet imagine, discoveries that will seem obvious in retrospect, but that require the knowledge base we are currently building. The investment in Mercury missions pays dividends not measured in the lifetime of any single mission, or even any single generation of researchers. That long view is difficult to maintain amid the pressures of annual budgets and political cycles. Space agencies must justify their existence repeatedly, defending exploration programs against competing priorities and skeptical legislators. Mercury missions are expensive, and their benefits are diffuse and long-term rather than immediate and concentrated. The case for Mercury exploration must be made not only on scientific grounds, but on grounds of technological development, international prestige, and inspiration for future generations of scientists and engineers. The arguments are real, but easily drowned out by more urgent concerns. Mercury science survives not because the political case is overwhelming, but because dedicated advocates make that case persistently. Building coalitions and securing funding one budget cycle at a time, the persistence has paid off. From Mariner 10's brief flyby in the 1970s through Messenger's years of orbital observations through Bepi Colombo's current operations, Mercury science has advanced despite being a minor component of the planetary exploration portfolio. The community is small but resilient, drawing talent from adjacent fields and maintaining institutional knowledge across the decades between major missions. Young researchers who started their careers analysing messenger data now lead analysis efforts for Bepi Colombo. Senior researchers who help design messenger instruments advise on future mission concepts that may not fly until after they retire. The generational continuity preserves expertise that would otherwise be lost, enabling the scientific community to extract maximum value from each precious dataset. The datasets continue to grow as Bepi Colombo's mission progresses. Each orbit adds observations that extend spatial coverage, temporal baseline, and measurement precision. The spacecraft's instruments operate according to carefully planned sequences designed to address high-priority questions, while remaining flexible enough to investigate unexpected discoveries. Ground controllers adjust those sequences in response to what the spacecraft reveals, directing attention to features that deserve closer examination and passing over regions that earlier observations characterized adequately. The mission is a collaboration between human judgment and robotic capability, with each contributing what the other cannot. Human judgment decides what questions matter, what observations might answer those questions, and how to interpret the results. Robotic capability performs measurements no human could survive making, transmits data across millions of kilometers of space, and operates autonomously when light speed delays make real-time control impossible. The combination is extraordinarily powerful, extending human senses to environments that human bodies cannot reach. Mercury exists for us only through this technological mediation, but the mediation is so seamless that scientists sometimes forget they are not looking directly at the planet, but rather at processed data representations that instruments and software produced. The forgetting is productive. It allows scientists to focus on the planet itself, rather than on the technological apparatus that makes observation possible. Yet the apparatus deserves occasional acknowledgement. The spacecraft orbiting Mercury represent the culmination of centuries of technological development, from the invention of the telescope through the development of radio communication through the creation of digital computers and precision sensors. Each component embodies knowledge accumulated across generations, solutions to problems posed by previous generations of engineers who could not solve them but could define them clearly enough for their successors to build upon. Bepi Colombo stands on the shoulders of every space mission that came before, learning from successes and failures alike. The spacecraft carries the legacy of the Mercury program and Apollo, of Mariner and Voyager, of every mission that expanded human presence beyond the atmosphere. That legacy is not merely historical interest. It is practical knowledge embodied in design decisions and operational procedures that keep the spacecraft functional in an environment that would destroy any less carefully engineered machine. Mercury orbits patiently as the spacecraft that studies it accumulates data, processes observations, and transmits results back to Earth. The planet neither knows nor cares that curious beings on a distant world seek to understand its nature. Mercury simply exists, responding to physical laws that govern its behavior whether or not anyone observes. The indifference is absolute, but the curiosity that drives observation is no less real for being ignored by its object. Scientists study Mercury because understanding is intrinsically valuable, because the universe rewards curiosity with knowledge, because each mystery solved reveals new mysteries that beckon investigation. The process continues until the last curious mind loses interest or dies, until the last functioning spacecraft fails, until the last civilization capable of planetary exploration turns its attention elsewhere or ceases to exist. For now, the curiosity remains vibrant. Mercury continues to fascinate those who take the time to look beyond the familiar worlds that dominate popular attention. The planet's strangeness is its gift, offering insights available nowhere else, and challenging scientists to expand their conceptual frameworks to accommodate what they find. The shrinking planet, still contracting after billions of years, still generating earthquakes that no seismometer has yet detected from orbit, still deflecting the solar wind with its anomalous magnetic field, remains one of the solar system's most compelling objects of study. Mercury earned its neglect through difficulty of observation and lack of obvious relevance to human concerns. It is earning its rehabilitation through the richness of the science it enables and the questions it forces scientists to confront. The confrontation continues with each new observation, each refined measurement, each model that fails to match reality and must be revised. Mercury does not yield its secrets easily. The planet guards them behind walls of radiation and temperature and distance that make every observation a technical triumph. But the secrets, once extracted, illuminate not just Mercury, but the processes that shaped all rocky worlds, the mechanisms that drive planetary evolution, the conditions that make some worlds habitable and others sterile. Mercury's secrets are the solar system's secrets, and unlocking them expands human understanding in ways that transcend the boundaries of any single world. The innermost planet will never be a destination for human footsteps, barring technological revolutions that seem implausible from our current vantage. But it need not be walked upon to be known. The robots we send in our place report back faithfully, translating alien landscapes into data streams that human minds convert into understanding. Through this remote collaboration, Mercury becomes as real to us as any place we might visit in person. Perhaps more real, because we see it through instruments more sensitive and persistent than human senses could ever be. The planet reveals itself gradually, reluctantly, but genuinely, and those patient enough to watch are rewarded with a world far stranger and more dynamic than anyone expected. The rehabilitation of Mercury from cosmic afterthought to scientific treasure represents something profound about the human relationship with the universe. For centuries, this world existed at the edge of human awareness, a dim point of light that appeared briefly before dawn or after sunset, noted by astronomers but rarely contemplated deeply. The ancient Greeks thought they saw two separate objects, a morning star and an evening star, before recognizing that a single planet played both roles. Even after that recognition, Mercury remained peripheral, overshadowed by Venus with its brilliant radiance, by Mars with its bloody colour and retrograde wanderings, by Jupiter and Saturn with their stately progressions through the zodiac. Mercury was too small, too dim, too fleeting to command sustained attention. That neglect persisted into the space age. When humanity began sending robots to explore the solar system, Mercury fell to the bottom of the priority list. Venus received multiple missions from both the Soviet Union and the United States. Mars became an obsession, hosting landers and rovers and orbiters in an increasingly sophisticated campaign of exploration. The outer solar system beckoned with its giant planets and fascinating moons, drawing Voyager on its grand tour and Galileo to Jupiter and Cassini to Saturn. Mercury waited, visited only once in passing, as if the solar system's innermost rocky world were merely an obstacle to navigate around rather than a destination worthy of study. The reasons for this neglect were practical and understandable. Mercury is genuinely difficult to reach, genuinely hostile to spacecraft, genuinely challenging to observe from Earth. Every mission to Mercury requires solving engineering problems that don't exist for missions to any other destination. The thermal environment, the orbital mechanics, the communication difficulties, the radiation exposure, all combine to make Mercury exploration expensive and risky. Space agencies with limited budgets and competing priorities naturally gravitated toward targets that offered more science per dollar, more certainty of success, more connection to questions that captured public imagination. The search for life focused attention on Mars and the icy moons. The study of atmospheres drew missions to Venus and Titan. The investigation of planetary rings sent spacecraft to Saturn. Mercury, lacking atmosphere, lacking moons, lacking any obvious relevance to astrobiology, attracted no constituency powerful enough to champion its exploration. Yet the very factors that made Mercury difficult also made it scientifically unique. No other world occupies Mercury's position in the solar system. No other body experiences the same intensity of solar radiation, the same extreme temperature variations, the same combination of size and density and orbital characteristics. Mercury is not merely one example of a rocky planet. It is an extreme example, a limiting case that tests theories developed to explain more moderate worlds. A theory of planetary formation that cannot account for Mercury is incomplete. A model of planetary interiors that fails when applied to Mercury is inadequate. A framework for understanding planetary evolution that breaks down at the inner edge of the solar system needs revision. Mercury's extremity is precisely what makes it valuable. The planet probes the boundaries of planetary science, revealing where established understanding holds firm and where it requires expansion. This realization drove the eventual decision to send Messenger, and it continues to drive the Bepi-Colombo mission, currently delivering new data. The scientific community recognized, after decades of focusing elsewhere, that Mercury held answers to questions that could not be addressed any other way. The planet's oversized core offered insights into differentiation processes and the distribution of elements in the early solar system. The volatile deposits at the poles challenged assumptions about what could persist on the innermost planet. The magnetic field, inexplicable by standard theories, demanded new models of dynamo generation in slowly rotating bodies. The lobate scarps, evidence of planetary-scale contraction, opened a window into thermal evolution that no other world offered as clearly. Mercury transformed from an afterthought into an essential component of comprehensive solar system science. The transformation reflects a broader pattern in scientific progress. Objects and phenomena initially dismissed as uninteresting often prove, upon closer examination, to hold crucial information. The apparent simplicity or familiarity of a subject conceals depths that reveal themselves only to sustained investigation. Mercury seemed simple because astronomers couldn't observe it well enough to perceive its complexity. The planet seemed boring because scientists lacked the conceptual frameworks necessary to appreciate what made it remarkable. As observational capabilities improved and theoretical understanding matured, Mercury's true nature became visible, and that nature proved far more interesting than anyone had assumed. The pattern appears throughout the history of science. Bacteria seemed irrelevant to chemistry, until their metabolic machinery revealed fundamental principles of biochemistry. Crystallography seemed like a niche concern until X-ray diffraction unlocked the structures of proteins and DNA. The cosmic microwave background seemed like noise until its analysis revealed the geometry and composition of the universe. Mercury joins this tradition of overlooked objects that turned out to matter profoundly. The planet's vindication stands as a reminder that the universe is full of phenomena we dismiss too quickly. That apparent simplicity often masks complexity we haven't yet learned to perceive. Bepi-Colombo's ongoing mission extends this process of revelation. Each data transmission adds detail to the emerging portrait of Mercury, filling gaps left by Messenger, resolving ambiguities that earlier observations could not address, discovering features that no one predicted. The spacecraft's two orbiters, working in complementary configurations, map the planet's surface and probe its depths with instruments more capable than any that came before. The magnetometer measures field variations too subtle for earlier sensors. The cameras resolve features too small for previous spacecraft to detect. The spectrometers identify compositional signatures that escaped prior analysis. Every improvement in instrumental capability translates into improved understanding of the world being observed. The data flowing back from Bepi Colombo will occupy scientists for years, perhaps decades after the mission ends. Raw observations must be calibrated and corrected, converted from engineering units to physical measurements. Individual measurements must be combined with others to build maps and models, each new addition refining the picture. Anomalies must be investigated, unexpected results verified, contradictions between different data sets resolved. The process is painstaking and often unglamorous, involving more spreadsheet work than moment of discovery. But it is through this patient accumulation of carefully analysed data that genuine understanding emerges, that Mercury transforms from a collection of observations into a coherent world with a comprehensible history and predictable behaviour. The scientists performing this work carry forward a tradition as old as natural philosophy itself. They join a lineage extending back through the astronomers who first measured Mercury's orbital parameters, through the observers who noted its phases and its transits across the Sun, through the ancient stargazers who tracked its appearances and named it for the messenger of the gods. That lineage will extend forward through future generations of researchers who will build on current work, using data gathered now to answer questions not yet formulated. Science is inherently intergenerational, each generation contributing what it can and passing the rest to successors better equipped to continue. The Mercury data being collected today will serve science long after everyone currently analysing it has retired or died. The investment of effort is an investment in the future of human knowledge. This intergenerational character of scientific work carries particular poignancy when applied to Mercury. The planet's own evolution unfolds on timescales that dwarf human civilization. The contraction that generates Labaert scarps has continued for billions of years and will continue for billions more. The cooling that drives this contraction began when Earth's crust was still molten and will persist until the Sun itself begins to fail. Individual human lifetimes, even the entire history of scientific observation, represent an infinitesimal fraction of the time over which Mercury changes. We glimpse the planet at one instant of its enormous history, extrapolating backward and forward using physical principles that we hope apply across spans of time our minds cannot truly comprehend. The mismatch between human timescales and planetary timescales creates a peculiar relationship between observer and observed. Mercury's earthquakes, generated by the ongoing contraction, occur unpredictably but regularly when measured against geological time. Thousands of quakes might occur each year, releasing the accumulated stress of continued shrinkage. Yet no human has ever detected one. Messenger lacked a seismometer. Bepi Colombo orbits too far away to register seismic vibrations. The quakes are real as the scarps that prove contraction happens, but they remain invisible to us, felt only by instruments we haven't yet invented or deployed. Future missions might carry seismometers to Mercury's surface, finally capturing the planet's tectonic heartbeat directly. Or the technical challenges might prove too great, leaving Mercury's seismicity forever inferred rather than measured. The uncertainty is part of what makes planetary science an adventure. We cannot know in advance which mysteries will yield to investigation and which will resist indefinitely. The adventure continues regardless. Human curiosity does not require guaranteed success to motivate exploration. Scientists pursue questions without knowing whether answers exist, without certainty that their methods will work, without assurance that their efforts will produce anything useful. The pursuit itself carries value, the engagement with the unknown, the attempt to push back the boundaries of ignorance. Mercury rewards this pursuit with discoveries that justify the effort, while simultaneously revealing new depths of ignorance to address. The cycle of question, investigation, partial answer, and new question continues indefinitely, or at least as long as curious minds remain to participate. The questions that Mercury raises extend far beyond the planet itself. Understanding how Mercury formed helps explain how all rocky planets form, including Earth. Understanding how Mercury's core generates its magnetic field illuminates dynamo processes that operate throughout the cosmos. Understanding how Mercury retains volatiles at its poles clarifies the behaviour of water and other compounds throughout the solar system. Understanding how Mercury's surface responds to micrometeorite bombardment and solar wind sputtering explains processes occurring on every airless body, from the Moon to asteroids to the moons of giant planets. Mercury serves as a natural laboratory for studying phenomena that occur universally, and the knowledge gained there transfers to contexts far removed from the innermost planet. This transfer of knowledge represents one of science's most powerful features. Understanding gained in one domain routinely proves applicable in others, often in ways that could not have been predicted in advance. The physics of Mercury's core connects to the physics of Earth's core connects to the physics of magnetic fields in stars and galaxies. The chemistry of Mercury's surface connects to the chemistry of lunar regolith, connects to the chemistry of asteroid surfaces, connects to the chemistry of interstellar dust. Every investigation exists within a web of connections that make isolated knowledge impossible. To study Mercury is to study the universe, one particular instance at a time. The web of connections also operates temporally. Mercury today carries information about the early solar system, about conditions that prevailed 4.5 billion years ago, about processes that shaped not just one planet, but all planets. The planet's composition reflects the distribution of elements in the solar nebula from which it condensed. Its structure reflects the violence of the accretion process and the giant impacts that characterize the solar system's youth. Its surface records the history of bombardment that all inner solar system bodies experienced. Reading Mercury's geological record is reading the solar system's history, accessing information preserved nowhere else in exactly this form. The reading is difficult. Mercury does not come with annotations or explanatory legends. Every feature must be interpreted through inference, comparing observation to expectation, generating hypotheses, testing them against additional data. The process is fallible. Scientists have been wrong about Mercury before and will be wrong again. Early observers thought they detected atmosphere. They were wrong. Astronomers believed for decades that Mercury's rotation synchronized with its orbit. They were wrong. Messenger data initially seemed to suggest certain compositional signatures that later analysis revised. Error is endemic to science, the inevitable companion of investigation at the boundaries of knowledge. But science has mechanisms for correcting error, feedback loops that eventually expose mistakes and replace them with better approximations of truth. Wrong hypotheses generate predictions that fail. Incorrect models produce inconsistencies that accumulate until they become undeniable. New data contradict established conclusions, forcing revisions that bring understanding closer to reality. The process is not infallible, sometimes taking longer than it should, sometimes requiring generational turnover before established views give way. But it works, over time, to bring human models of the universe into better alignment with how the universe actually operates. Mercury's scientific history exemplifies this self-correcting tendency. Each generation's understanding has improved on its predecessors, not because later scientists were smarter, but because they had access to better data and could build on previous work. The improvement will continue as long as exploration continues. Bepi Colombo's data will enable models more accurate than those based on Messenger alone. Future missions, if they occur, will enable models more accurate still. Each iteration brings Mercury's portrait into sharper focus, revealing details invisible to earlier observers, confirming some hypotheses while overturning others. The portrait will never be complete. The universe contains more detail than any finite number of observations can capture, but it will become increasingly faithful, increasingly useful for understanding not just Mercury, but the planetary processes that Mercury illustrates. The value of this understanding transcends practical application. Some knowledge serves human needs directly, enabling technologies that improve life or warning of dangers that threaten it. Mercury knowledge generally does not fall into this category. No one's daily life will change because scientists better understand how lobate scarps form. No policy decision depends on precise measurements of Mercury's core diameter. The planet is too remote, too hostile, too irrelevant to human affairs to offer practical benefits in any conventional sense. Yet the knowledge matters anyway. Understanding the universe is a distinctly human activity, perhaps the most distinctly human activity, the thing that most clearly separates our species from all others that share this planet. We alone ask questions about the nature of distant worlds. We alone build instruments to answer those questions. We alone accumulate knowledge across generations, each cohort adding to what its predecessors bequeathed. This capacity for cumulative understanding represents something precious, something worth cultivating regardless of whether it produces useful technologies or economic benefits. Mercury exploration expands human understanding, and that expansion is inherently valuable, requiring no further justification. The innermost planet, shrinking slowly in the cosmic furnace, guards no treasures that humans might exploit. Its surface offers no resources worth the expense of extraction. Its environment permits no colonization, no permanent human presence, no transformation into a second Earth. Mercury will never be humanity's home, or humanity's mine, or humanity's stepping stone to greater things. The planet offers only knowledge, only the chance to understand one more corner of the universe, only the satisfaction of curiosity that evolution instilled in us long before we knew how to satisfy it systematically. That offering is enough. The knowledge Mercury provides enriches human civilization in ways that transcend material benefit. It expands our sense of what exists, our awareness of the cosmic context we inhabit, our appreciation for the extraordinary processes that shape the worlds around us. A species that understands Mercury is wiser than one that does not because the understanding is useful, but because understanding itself is a form of flourishing, a fulfillment of capacities that make us human. Mercury exploration is an exercise in becoming more fully what we are, curious creatures reaching outward to comprehend a universe that does not explain itself. The reaching will continue. As long as questions remain unanswered and instruments remain capable of gathering data, scientists will study Mercury. Future missions will build on Bepi Colombo as Bepi Colombo built on Messenger, and Messenger built on Mariner 10. The accumulated understanding will grow, the models will improve, the mysteries will yield one by one to sustained investigation. Some mysteries will prove more stubborn than others. Some may never yield at all, protected by practical limitations that no foreseeable technology can overcome. But the attempt to understand will persist, driven by the same curiosity that motivated the first human to wonder why a point of light appeared at dawn and vanished shortly after. Mercury neither knows nor cares about this attention. The planet responds only to physical forces, gravitational and electromagnetic and thermal, continuing its eternal dance around the sun regardless of whether any mind observes. The indifference is complete. Yet something remarkable happens when a curious species turns its attention to an indifferent world. The universe becomes known to itself. Through human minds contemplating Mercury's nature, the cosmos achieves a form of self-awareness it could not possess otherwise. We are the universe's way of understanding itself, and Mercury is one of the things we help the universe understand. The responsibility this implies is both humbling and ennobling. We are small, brief, fragile creatures clinging to a mote of rock in an incomprehensibly vast cosmos. Yet we are also the only beings we know of who ask questions about that cosmos, who build instruments to answer them, who accumulate understanding across generations and pass it forward. Mercury exploration expresses this dual nature perfectly. We are too small to visit the innermost planet in person, too brief to watch its slow contraction unfold, too fragile to survive its hostile environment. But we're curious enough to send robots in our place, patient enough to wait years for data to arrive, clever enough to extract understanding from streams of numbers transmitted across millions of kilometers. The contradiction resolves in the act of exploration itself. We are small, but we reach beyond our smallness. We are brief, but we contribute to an enterprise that spans generations. We are fragile, but we build machines that survive environments that would kill us instantly. Mercury exploration celebrates human capability precisely because it pushes against human limitation. Every observation returned from the innermost planet represents a victory over the constraints that would, if we accepted them, confine us to our immediate surroundings and leave the universe forever unknown. The victories accumulate. Each datum adds to the store of knowledge. Each refined measurement improves the accuracy of models. Each new discovery reveals aspects of reality previously hidden. Mercury emerges from these accumulating victories as a world comprehensible in ways that would have astonished observers of any previous century. We know, now, things about the innermost planet that no human could know before, things that required technologies and theories and methods that didn't exist until recently. The knowledge is ours. belonging to the species that created it, available to anyone curious enough to seek it out. The creation continues as Bepi Colombo pursues its mission, as scientists analyse the data it provides, as theorists construct models to explain what observations reveal. Mercury yields its secrets reluctantly, but it yields them. The planet that seemed too difficult and too boring to bother with has become a source of profound scientific insight, a world that challenges assumptions and expands understanding. The rehabilitation from afterthought to treasure is complete, or nearly so. Mercury will never capture public imagination the way Mars does, will never inspire the same sense of wonder that images from Jupiter or Saturn evoke. But among those who study rocky worlds and seek to understand how planets work, Mercury has earned its place as one of the solar system's most fascinating objects. The fascination will persist as long as mysteries remain, and mysteries will remain for as long as humans care to investigate. Mercury keeps its secrets behind barriers of radiation and heat and distance, revealing them only to those patient enough to mount the expeditions necessary to extract them. The patience required is substantial. Decades pass between missions. Careers span the intervals. Scientists who proposed Messenger as young researchers are now senior figures in their fields, passing knowledge to successors who will carry the work forward. The rhythm of planetary exploration is slower than human impatience prefers, but it is the rhythm that reality permits. Mercury exploration proceeds at the pace allowed by funding and technology and orbital mechanics, and those who participate accept the pace as the price of admission. The price is worth paying. Mercury, the planet nobody talks about, the world dismissed as too difficult and too dull to merit attention, has proven itself one of the solar system's most rewarding subjects of study. The shrinking planet, still contracting after 4 billion years, still generating features that reshape its surface, still guarding a magnetic field that defies easy explanation, offers lessons that apply far beyond its cratered terrain. Every discovery at Mercury illuminates processes that operate throughout the cosmos. Every mystery solved there provides tools for solving mysteries elsewhere. The innermost planet, smallest and strangest of the rocky worlds, contributes to human understanding in ways that far exceed its modest size. And so, the work continues. Spacecraft orbit, data flows, scientists analyse, understanding grows. Mercury reveals itself grudgingly to those who make the effort to look. The planet that seemed least worthy of attention has earned its place among the solar system's most compelling objects of study. The rehabilitation is complete. Mercury is no longer the afterthought of planetary science. It is a treasure, a natural laboratory, a source of insights available nowhere else. The innermost planet has finally, after centuries of neglect, received the attention it deserves. In the end, Mercury teaches a lesson that extends far beyond planetary science. The things we dismiss often prove, upon closer examination, to hold value we could not perceive from a distance. The objects we neglect frequently reward investigation with discoveries we could not have predicted. The universe is larger and stranger, and more interesting than our assumptions allow, and the only way to discover this is to examine what we have overlooked. Mercury stood for millennia at the edge of human awareness, noticed but not truly seen, observed but not understood. The decision to look more closely, to send spacecraft and build instruments, and devote careers to studying this small, hostile, difficult world has repaid itself many times over in knowledge gained and understanding deepened. The lesson applies to everything. The universe conceals treasures everywhere, hiding them in plain sight, waiting for curious minds to notice and investigate. Mercury was always there, always fascinating, always full of secrets worth uncovering. It only seemed boring because we hadn't learned how to appreciate its strangeness. The planet hasn't changed. Our understanding has changed. And that change, that growth in comprehension, represents something precious, something worth celebrating, something that justifies the expense and effort and patience that planetary exploration requires. Mercury orbits on, indifferent to human attention but faithfully yielding data to those who seek it. The innermost planet shrinks imperceptibly, cools gradually, shakes occasionally, reflects sunlight perpetually. It will continue doing these things long after the last spacecraft fails, and the last scientist retires, and the last civilization capable of planetary exploration fades from existence. But for now, in this brief window when curious beings have the means to investigate, Mercury offers itself for study. The offering is precious. The knowledge gained enriches not just science, but humanity itself, expanding our sense of what exists and how it works and where we fit within the vast cosmic tapestry. The planet nobody talks about has become the planet that reveals the solar system's deepest secrets to those patient enough to listen. Mercury, smallest and strangest and most extreme of the rocky worlds, has earned its rehabilitation through the sheer richness of the science it enables. The afterthought has become essential. The overlooked has become cherished. And somewhere, in the cosmic furnace where temperatures swing between inferno and absolute cold, where craters preserve ancient histories and scarps record ongoing contraction, the innermost planet continues its lonely orbit, waiting for the next question, guarding the next secret, offering the next reward to those bold enough to seek it out.